We have mapped less than 25% of the global seafloor in high resolution, and over 80% of the ocean remains unexplored, unseen by human eyes. Allow your breathing to slow as the gentle sounds begin, and let your body sink into the quiet. We are going somewhere. There is time. The lights can stay dim. This vast darkness exists because the crushing pressure and absolute cold of the deep create a frontier more difficult to reach than the surface of the moon. New sonar technologies and deep-sea submersibles have only just begun to trace the outlines of hidden mountain ranges, abyssal plains, and living communities that thrive without sunlight. Tonight we drift into that silent world, where the unknown still breathes. The ocean holds a volume of water so immense it defies easy comprehension, some 1.335 billion cubic kilometers stretching across the globe. Yet within this vast blue sphere, the true shape of the seafloor remains one of our planet's most stubborn mysteries. More than 80% of it has never been mapped in detail, leaving a hidden landscape that is still largely a blank page in our scientific record. The reason satellites cannot chart the seabed is fundamental. Seawater is virtually opaque to the electromagnetic signals they rely on. Radar and optical sensors can map the surfaces of Mars or the Moon in exquisite detail, but they cannot penetrate the water column. Instead, satellites infer the shape of the seafloor indirectly by measuring tiny bumps and dips in the ocean surface, caused by the gravitational pull of underwater mountains and trenches. This method produces a very coarse sketch, missing anything smaller than several kilometers across. The result is a startling contrast in cartographic knowledge. We possess sharper, more complete maps of the Moon and Mars than we do of our own ocean floor. The entire lunar surface has been mapped to a resolution of about 100 meters, and Mars has been imaged down to 20 meters or better. Meanwhile, the global map of the seafloor derived from satellite gravity has a resolution of roughly 5 kilometers, meaning an entire mountain range could be hiding beneath a single pixel. Only around 20% of the ocean floor has been surveyed by ships using modern sonar, which can reveal features just a few hundred meters across. To close this gap, a monumental international effort known as the Seabed 2030 project has set out to map the entire ocean floor by the end of this decade. It is a collaboration between governments, research institutions, and industry, gathering data from survey vessels, autonomous underwater vehicles, and even fishing boats. The goal is to create a definitive high-resolution map that will finally reveal the planet's last great wilderness in its full complexity. The visual void is even more profound. The deep sea floor, covering the vast majority of the ocean basin below 200 meters, has barely been glimpsed by any camera or human eye. It is estimated that less than 0.05% of this realm has ever been visited by a camera or a remotely operated vehicle. The rest remains a silent, lightless world, known only through the faint gravity signatures that ripple the sea surface far above. Every year, a few thousand square kilometers of new seafloor are mapped in detail, a pace that turns the complete survey into a work of generations. Each new expedition reveals seamounts, canyons, and ecosystems that rewrite our understanding of geological processes and life's resilience. The unmapped floor is not merely an absence of data. It is a reminder that the Earth still holds places where the unknown begins, just a few hundred meters beneath the waves. For centuries, the ocean's depths remained a realm of pure conjecture, measured only by the length of a weighted rope dropped over the side of a ship. The first truly systematic attempt to map this abyss came with the voyage of HMS Challenger between 1872 and 1876. This British corvette, retrofitted as a floating laboratory, crisscrossed the globe, lowering miles of hemp line weighted with cannonballs to take the first scattered soundings of the deep-sea floor. The crew discovered vast plains of Globigerina ooze and the first hint of a great trench in the western Pacific, a depression they measured at over 8,000 meters, a depth that seemed almost impossible. The method of sounding with a line was agonizingly slow and imprecise, often taking hours for a single reading. A breakthrough arrived in the 1920s with the development of echo sounding, a technique that sent a pulse of sound from the ship and measured the time it took for an echo to return from the bottom. This allowed for continuous profiles of the seafloor beneath a moving vessel, revealing for the first time the broad, rolling contours of the abyssal plains. The German meteor expedition of the mid-1920s used this new technology to map the South Atlantic, discovering the Mid-Atlantic Ridge, a vast underwater mountain range that no one had known existed. Yet even echo sounding in its early form painted a deceptively simple picture of the ocean floor, suggesting a world of gentle slopes and gradual rises. The true complexity of the abyss remained hidden until the years after World War II, when highly sensitive military sonar developed for detecting submarines was turned toward scientific ends. This technology, coupled with the precision of acoustic navigation, revealed a landscape of jagged canyons, towering seamounts, and deep fracture zones that crisscrossed the ocean basins. The seafloor was not a quiet, monotonous desert, but a dynamic and violently sculpted terrain. As the technology improved, so too did the records of maximum depth, each new reading pushing the known limit of the ocean deeper. The first truly precise measurement of the Challenger Deep, the deepest known point in the Mariana Trench, was taken in 1951 by the British survey ship HMS Challenger II, which recorded a depth of over 10,800 meters using echo sounding. This record was soon surpassed by the Soviet research vessel Vityaz, which in 1957 measured a depth of more than 11,000 meters in the same trench. Each new record was a testament to the increasing ingenuity of the instruments and the perseverance of the explorers. The culmination of this era of depth records came in 1960, when the Swiss-designed bathyscaphe Trieste descended to the bottom of the Challenger Deep, carrying 2 men into a place no human had ever been. The pressure gauge on board read a depth of 10,916 meters, a figure that would stand as the official deepest point for decades. For the first time, humanity had not only measured the depth, but had witnessed the abyss directly, a world of utter darkness and immense pressure, yet surprisingly alive with a flatfish and a shrimp. The story of measuring the ocean's depth is not one of a single final discovery, but a gradual revelation of scale and complexity. Each generation of instruments, from the sounding line to the echo sounder to the multi-beam sonar, has peeled back another layer of obscurity. What began as a simple question of how deep the water is has become a detailed map of the planetary engine that drives currents, shapes climate, and harbors life in forms we are only beginning to understand. The ocean floor, once a blank, is now a known world, though its deepest secrets remain as vast and dark as the water itself. The ocean is a realm of immense and patient secrecy, a blue expanse that covers most of our planet, yet holds back the shape of its own inner life. Scientists estimate that 91% of all marine species remain undiscovered, a vast hidden multitude of forms and behaviors. This figure is not a guess, but a calculation rooted in the steady pace of discovery and the enormous unexplored volume of the sea. Each year, around 2,000 new marine species are formally described and given a name. These range from brightly colored reef fish to translucent crustaceans and deep-dwelling worms. At this rate, it would take many centuries to approach a complete inventory of life in the water column and on the seafloor. The task is monumental, and the ocean yields its secrets with a quiet, unhurried rhythm. The deepest reaches of the ocean are the greatest reservoir of the unknown. Most of the species yet to be found will emerge not from sunlit shallows, but from the abyssal plains, seamounts, and hydrothermal vent fields miles below the surface. Here, in the crushing darkness, life has taken forms that challenge our understanding of biology, sustained by chemosynthesis and adapted to pressures that would dissolve the structures we know. On land, the catalog of life is far more complete. We have described the vast majority of mammals, birds, reptiles, and flowering plants, and our terrestrial biosphere feels to us largely mapped and named. The contrast with the ocean is stark. We have scrutinized the surface of Mars in finer detail than we have surveyed much of our own seafloor, and the living contents of that marine world remain a deep, abiding question. New discoveries arrive with every expedition. Gelatinous siphonophores drift through the midwater, bone-eating worms colonize the skeletons of whales, and fish with hand-like fins walk along the sediment. These are not rare anomalies, but signals of entire ecosystems built on rules we are only beginning to parse. Every creature pulled from the depths is a reminder that the book of marine life is still mostly blank pages. The ocean holds its unnamed multitudes in a silence that is older than humanity. The slow and careful work of naming them is a form of listening, a scientific patience that matches the tempo of the deep. We are only just beginning to understand the true scale of life on our own planet, and the sea remains the largest, most patient keeper of that mystery. The ocean welcomes us at its surface with a pressure of 1 atmosphere, the weight of the entire column of air above. For every 10 meters we descend, the water column adds another full atmosphere of pressure. At 40 meters, a recreational diver already breathes air at 5 times the surface pressure, and the body begins to whisper its physiological limits. The descent is a quiet, relentless multiplication of force, invisible and patient. At 6,000 meters, the pressure reaches 600 atmospheres. To understand this, imagine a human thumb, roughly 2 square centimeters in area, and then place upon it the weight of a large saloon car. At such depths, any gas-filled cavity, from a lung to a small air bubble in a wooden splinter, is compressed to a fraction of its volume. Materials that are porous or air-filled implode instantly, and even the dense syntactic foams used in deep-sea vehicles must be engineered with microscopic glass spheres to resist collapse. Most of the ocean lies permanently beyond the reach of recreational diving. The average depth of the global ocean is nearly 3,700 meters, a realm where pressure exceeds 370 atmospheres. Even the most elite technical divers, breathing exotic gas mixtures, venture only to the very edge of the twilight zone, rarely beyond 150 meters. The vast, dark volume of the deep sea, making up over 95% of Earth's habitable space, is a place where the unprotected human body would be crushed to a dense, unrecognizable form in a fraction of a second. Building a vessel to withstand the Hadal zone, the deep trenches between 6,000 and 11,000 meters, requires a marriage of perfect geometry and uncompromising materials. The pressure hull, typically a sphere, must be forged from a single block of titanium alloy, its wall thickness growing to over 1/3 of its inner diameter. Every square centimeter of the hull at Challenger Deep, where the pressure approaches 1,100 atmospheres, endures a load equivalent to the weight of a small elephant. The smallest flaw in the metal, a microscopic crack or an imperfect weld, becomes the seed of a catastrophic implosion that can obliterate the craft in microseconds. The engineering challenges extend far beyond the simple crushing strength of the hull. The sphere must be perfectly buoyant yet robust, so it is often paired with a jacket of syntactic foam, a composite of glass microspheres in epoxy, which can resist compression while providing lift. Viewports emerge as critical weak points and are crafted from thick, conical acrylic plastic that wedges itself tighter against its seat as the pressure mounts. Even the electrical systems cannot be sealed in air-filled boxes. They are submerged in an insulating oil that is pressure compensated, so the pressure inside matches the crushing force outside. The deep ocean remains a frontier defined by this silent, omnipresent pressure. It is a place where the very physics of our world sets a barrier more formidable than the vacuum of space. While robots have begun to map these depths, the number of human beings who have seen the Hadal trenches with their own eyes is fewer than those who have walked on the moon. The crushing embrace of the abyss keeps its secrets closely, yielding them only to the most exquisite feats of engineering and human ingenuity. In the early 1930s, the ocean depths remained as foreign as the surface of the moon, and 2 men, William Beebe and Otis Barton, decided to see them for themselves. They designed the bathysphere, a steel sphere with small quartz windows, lowered on a steel cable from a ship. In 1934, off the coast of Bermuda, they descended to a depth of 3,028 feet, a record that would stand for nearly 2 decades, peering into a world of bioluminescent fish and strange, drifting creatures. The bathysphere was tethered and fragile, but a new generation of vehicles sought to break free from the cable. The Trieste, a bathyscaphe designed by Auguste Piccard, used a large float filled with gasoline for buoyancy and a heavy iron shot for ballast. In January 1960, Jacques Piccard and Don Walsh guided the Trieste into the Challenger Deep of the Mariana Trench, reaching a depth of 35,814 feet, a place where the pressure exceeds 1,000 atmospheres. They spent only 20 minutes on the bottom, their view limited by a single port, but they had proven that humans could reach the deepest point on Earth. The Trieste was a pioneer, but it was large, unwieldy, and able to carry only a single observer. A more practical vehicle came in the form of Alvin, a submersible built for the Woods Hole Oceanographic Institution and launched in 1964. It was smaller, more maneuverable, and could carry a pilot and 2 scientists. In 1977, Alvin made its most famous discovery, diving to the Galapagos Rift and revealing hydrothermal vents, entire ecosystems thriving on chemical energy in the darkness of the deep sea, a discovery that revolutionized biology. For decades after Alvin, the community of deep submersibles remained small, limited by the immense engineering challenges of operating under crushing pressure. Most vessels, like the Japanese Shinkai 6500 or the Russian Mir, could only reach depths of around 20,000 feet. The full ocean depth, the abyssal trenches below 30,000 feet, remained accessible only to a handful of specialized vehicles, and even then, only for brief, costly missions. A new era began in the 21st century with the advent of modern materials and engineering. The limiting factor, a commercial submersible built by Triton Submarines and piloted by Victor Vescovo, is a two-person vehicle with a pressure hull made of a titanium alloy that can withstand the full pressure of the ocean. In 2019, it made multiple dives to the Challenger Deep, and it has since visited the deepest points of all 5 of the world's oceans. It is the first vehicle to be certified for repeated dives to full ocean depth, a significant shift from the one-off expeditions of the past. Yet for all this progress, the number of vehicles capable of reaching the deepest trenches remains astonishingly small. Fewer than a dozen submersibles in the world can dive below 6,000 meters, and the fleet of true full ocean depth vessels can be counted on one hand. The cost of design, construction, and maintenance, combined with the extreme technical demands, means that exploration of the abyss remains a rare and privileged undertaking, a frontier that is only slowly giving up its secrets. While your phone displays the time, a deep-sea coral that began growing before the invention of writing is still alive on an unmapped seamount. A remotely operated vehicle is essentially a highly maneuverable underwater robot, connected to a surface vessel by a long, load-bearing tether. This cable delivers power and carries fiber optic strands that stream high-definition video and control signals in real time, allowing a pilot on the ship to see exactly what the machine sees. The pilot manipulates joysticks and consoles while watching a bank of monitors, guiding the vehicle's thrusters, manipulator arms, and sampling tools with surgical precision. Without this physical link, instantaneous two-way communication would be impossible in the ocean's depths, where radio waves simply cannot travel. Most commercial work-class ROVs are designed to operate down to 3,000 or 4,000 meters, a depth range that covers the vast majority of subsea infrastructure and the upper reaches of the continental slope. Beyond this, the crushing pressure demands exotic materials and extraordinarily precise engineering, which limits the fleet of vehicles capable of reaching 6,000 meters to a handful of scientific machines. Only a tiny number of specialized ROVs and landers have ever touched the true deep, the 11,000-meter trenches, and each such dive is a major event in engineering history. An autonomous underwater vehicle, by contrast, cuts the tether entirely. It is pre-programmed with a mission plan and then released into the ocean, where it navigates with inertial guidance and acoustic positioning, swimming silently for hours or days. Unable to send live video back to a human operator, the AUV compensates by running powerful multi-beam sonars that paint the seafloor in exquisite detail, revealing underwater mountains, ancient shipwrecks, and the texture of the abyssal plain. When it surfaces and is recovered, the data it carries can be stitched into vast, high-resolution maps that no tethered vehicle could ever survey with the same efficiency. The expense of operating in the deep ocean is the single greatest barrier to exploration. A fully equipped research vessel with a deep-rated ROV or AUV typically costs between $50,000 and $100,000 per day, a figure that encompasses fuel, crew, insurance, and the salaries of highly specialized technicians. Even a modest 2-week expedition can therefore consume $1 million, a sum that must be secured years in advance from national science budgets or private philanthropy. Every hour over the side is precious, and weather, mechanical failure, or a lost vehicle can erase a season's work in a moment. The result of these financial and logistical pressures is that the number of deep dives conducted each year remains astonishingly small. In any given year, the global community might send vehicles capable of reaching 6,000 meters on only a few dozen expeditions, and the deepest points on Earth see human presence or robotic contact perhaps once or twice annually. The vast majority of the seafloor below 3,000 meters, which covers more than half the planet's solid surface, has never been photographed, let alone visited. This is a quiet, almost unnoticed fact of our modern world. What machines can achieve in the deep is remarkable, yet their limitations are equally stark. An ROV can gaze at a hydrothermal vent in real time and delicately collect a rock sample, but it cannot make rapid decisions when faced with unexpected terrain without constant human guidance. An AUV can map 1,000 square kilometers on a single battery charge, yet it will never observe a fleeting biological event as it unfolds. Together, tethered and autonomous vehicles form a complementary pair, one offering presence and dexterity, the other offering endurance and perspective, but both are constrained by an environment that remains, and will long remain, profoundly inhospitable to our most ambitious technology. In the early months of 1977, a research vessel named Canoe sailed to a restless patch of seafloor in the eastern Pacific, some 400 kilometers northeast of the Galapagos Islands. This was a region where the Earth's tectonic plates were slowly pulling apart, and the expedition's geologists hoped to probe the volcanic and hydrothermal processes shaping the ocean crust. A deep submergence vehicle called Alvin was prepared for a series of dives, its titanium hull designed to carry a pilot and 2 observers into the crushing darkness 2.5 kilometers below the surface. The expectations were modest, shaped by a century of deep-sea biology that depicted the abyssal plain as a quiet desert nourished only by a faint rain of organic debris from the sunlit world above. On the afternoon of February 17th, Alvin descended through the cold, clear water with pilot Jack Corliss and scientists John Edmund and Tanya Atwater aboard. The temperature probe they trailed began to twitch, registering small, unexpected spikes of warmth near the seabed. As the submersible's light swept across the basaltic terrain, the observers saw something that defied all reason. Thickets of ghostly white tubes, some taller than a person, clustered around shimmering, mineral-rich fluids that rose from spire-like chimneys. Where they had expected bare rock and the occasional scavenger, they found a dense living garden, a vision so improbable that the first voice crackling over the intercom to the surface ship simply reported, "We've got a whole new ballgame down here." Dominating this hidden oasis were the giant tube worms, Riftia pachyptila, creatures that had no mouth, no gut, and no anus, yet grew with astonishing speed to lengths exceeding 2 meters. Their chalky white tubes were crowned with brilliant red plumes, feathery structures rich in hemoglobin, swaying gently in the vent fluid. Around them, thick carpets of blind white clams and dense swarms of glistening mussels clung to the warm rock, while pale, ghostly crabs picked their way among the colonies. Every available surface was encrusted with life, forming a self-contained metropolis that owed nothing to the sun. The sheer abundance of animals in this sunless realm presented a profound biological paradox. On the surface, all complex food webs rest on the ability of plants and algae to capture sunlight through photosynthesis. But here, no photon had ever penetrated. The key lay in the vent water itself, a cocktail of dissolved minerals and gases that included hydrogen sulfide, a compound highly toxic to most organisms. Scientists soon realized that certain bacteria were harvesting energy not from light, but from the chemical reaction between sulfide and oxygen in the seawater, a process we now call chemosynthesis. These microbes were the true primary producers of the vent ecosystem, forming the base of a food chain that operated in absolute darkness. The giant tube worms, it turned out, had evolved a remarkable pact with these chemosynthetic bacteria. Inside a specialized organ called the trophosome, which filled most of the worm's body, they housed billions of microbes, providing them with sulfide absorbed by the red plume and oxygen transported by their unique hemoglobin. In return, the bacteria fed their host with organic carbon, effectively turning the worm into a self-sufficient living factory. The clams and mussels possessed similar symbiotic relationships, their gills packed with bacteria that allowed them to thrive in the very fluids that would poison ordinary animals. This was not a marginal, struggling community, but a highly evolved, intricately balanced world. The Galapagos Rift discovery did more than add a new chapter to marine biology. It shattered the fundamental assumption that the sun is the sole engine of life. For the first time, we had proof that an entire ecosystem could be powered by the planet's internal chemistry, a realization that rewrote the textbook definitions of habitable environments. It opened a new window onto the origins of life on our own planet, suggesting that the first organisms might have emerged not in sunlit pools but around deep, dark, chemically rich vents. And it transformed the search for life beyond Earth, offering a plausible model for how organisms might survive in the hidden oceans of icy moons like Europa or Enceladus, where sunlight is a distant memory but water, rock, and chemical energy may yet endure. Deep beneath the ocean surface, where sunlight never penetrates, A different kind of life thrives on a fuel that is invisible and toxic to most creatures. This process is chemosynthesis, a biological alchemy in which certain bacteria convert chemical energy into organic matter. Unlike photosynthesis, which captures the energy of photons, chemosynthesis harvests the energy locked in compounds such as hydrogen sulfide that billows from fissures in the seafloor. The discovery of this dark metabolism reshaped our understanding of the fundamental requirements for life. At the heart of a hydrothermal vent field, superheated water rich in dissolved minerals and hydrogen sulfide erupts from the crust. Chemosynthetic bacteria, often living freely in the shimmering fluids or as dense mats, oxidize the hydrogen sulfide using oxygen dissolved in seawater. The reaction releases energy that the bacteria harness to fix inorganic carbon, building the sugars and proteins that form their own cells. In this way, the vent fluid becomes a primitive fuel, and the bacteria become the primary producers of an ecosystem that exists in perpetual night. From these microscopic chemosynthetic pioneers, a rich and alien food web unfolds. Giant tube worms, lacking a mouth or gut, house billions of symbiotic bacteria within a specialized organ called the trophosome. The worms transport hydrogen sulfide and oxygen to their internal guests and receive nourishment in return. Clams and mussels also cultivate these bacteria on their enlarged gills, while grazing snails, shrimp, and crabs feed on the bacterial mats. Predators such as octopus and zorsid fish arrive to hunt the grazers, and the entire community depends on the continuous chemical harvest at the vent. The same principle sustains life beyond the scalding vents. Along continental margins, cold seeps release methane and hydrogen sulfide at ambient sea temperatures, supporting dense beds of tube worms, clams, and carbonate structures built by microbial activity. When a whale carcass settles on the abyssal plain, its enormous skeleton becomes a feast. As the bones decay, sulfate-reducing bacteria produce hydrogen sulfide, fueling a chemosynthetic ecosystem that can persist for decades. Hydrothermal vents themselves are not isolated phenomena, but line the mid-ocean ridges, volcanic arcs, and back arc basins that girdle the planet, forming a global network of chemical oases. This revelation that complex ecosystems can flourish entirely independent of the sun has profound implications for the limits of habitability. For more than a century, the tree of life was thought to be rooted in solar energy. The vent communities demonstrated that the engine of life could be entirely geological, driven by the planet's internal heat and chemistry. The deep biosphere, nourished by chemosynthesis, may even extend into the porous rock of the oceanic crust, a hidden realm of microbial life that operates on geological timescales. The existence of chemosynthetic ecosystems has become a guiding light in the search for life beyond Earth. On Jupiter's moon Europa, a subsurface ocean likely contacts a rocky seafloor, where tidal flexing could generate hydrothermal activity and release chemical reductants. Saturn's moon Enceladus ejects plumes of water, silica nanoparticles, and molecular hydrogen directly into space, hinting at active serpentinization reactions on its ocean floor. The life that sways in the darkness of our own deep sea now stands as a model for what we might one day find beneath the icy shells of distant ocean worlds. In the absolute darkness of the deep ocean, where sunlight never penetrates, life has found a way to create its own light. Recent surveys suggest that an estimated 76% of all animals living in the water column beyond the reach of the sun are capable of bioluminescence. This silent, cold chemistry illuminates the largest habitat on Earth, turning the abyss into a vast constellation of living signals. The most common mechanism behind this light is a chemical reaction between a light-producing molecule called luciferin and an enzyme, luciferase. When these two substances meet in the presence of oxygen, they release energy as a cool, visible glow, often with astonishing efficiency. This reaction can take place inside the animal's own cells, triggered by nerve impulses that control the exposure of the luciferin to the enzyme. A different strategy relies on a partnership with luminous bacteria. The deep-sea anglerfish is perhaps the most famous host, cultivating a dense population of glowing microbes within a specialized lure-like appendage that dangles above its jaws. The fish carefully nurtures these bacteria in a light organ, which receives a rich supply of nutrients and in return the bacteria produce a steady beacon that the anglerfish uses to draw curious prey close to its needle-sharp teeth. For many creatures, survival depends on hiding in plain sight, and bioluminescence provides a counterintuitive form of camouflage known as counterillumination. By producing a gentle glow on their undersides, animals like hatchetfish and certain squid can match the faint downwelling light from the sky, effectively erasing their silhouettes from predators lurking below. This biological trick turns a vulnerable shadow into a seamless extension of the twilight sea. Beyond concealment, light serves as a sophisticated language. Specific patterns, colors, and flash durations act as species-specific signals, allowing animals to find mates in the vast, empty expanse. From the intricate courtship spirals of tiny ostracods to the species recognition codes of dragonfish, the deep sea is filled with silent conversations written in points of blue and green light. The same chemistry is also a weapon. A sudden burst of light can startle a predator, buying precious seconds for escape, or act as a burglar alarm that attracts a larger predator to the attacker. The vampire squid, for instance, releases a cloud of sticky, glowing mucus rather than ink, while the stoplight loosejaw uses a red beam of light, invisible to almost all other deep-sea animals, to illuminate its prey without being detected. More than 80% of the global ocean remains unmapped and unseen, a volume so immense that each expedition can still redraw the boundaries of known biology. To understand how this vast system functions, scientists often focus on its vertical layers, where the rules of life are rewritten by the fading of light and the slow accumulation of pressure. The organisms drifting through the twilight mesopelagic, the lightless bathypelagic, and the crushing Hadal trenches are not isolated enigmas. Their strange metabolisms and migrations carry the signatures of nutrient cycles that link the sunlit surface to the seafloor. Beneath the skin of the sunlit ocean, the world begins to change within the first 200 meters. Sunlight, which moments ago danced in brilliant shafts, frays into a deepening blue, and then surrenders entirely to an eternal dusk. This is the mesopelagic zone, a realm where the last violet and blue wavelengths are absorbed, leaving a darkness so complete that the human eye perceives only an abyss. Here, life has not merely endured, but has shaped itself into forms of quiet astonishment. Lanternfish, among the most abundant vertebrates on the planet, carry constellations of light along their flanks, using photophores to camouflage their silhouettes against the faint glow from above. Hatchetfish compress their silver bodies to a razor thinness, their upward-facing eyes scanning for the faintest shadow of prey. Drifting among them, siphonophores string together colonies of specialized bodies, some pulsing with gentle propulsion, others trailing stinging tentacles like fine silk threads in the dark. Each evening, as the solar light fades from the surface, a signal ripples through this twilight world and triggers the largest animal migration on Earth. Countless tons of life, from the thumb-sized lanternfish to delicate gelatinous forms, begin a slow ascent of hundreds of meters. They rise to feed in the relative safety of the night-lit surface waters, returning to the depths before dawn to avoid predators that rely on daylight vision. This nightly pilgrimage is far more than a feeding ritual. It is the engine of a vast biological pump. In the surface layers, the migrants consume carbon-rich plankton, and upon their return to the mesopelagic, they respire, excrete, and eventually die, releasing that carbon into the deep sea. This transport of organic matter from the sunlit surface to the ocean's interior sequesters millions of tons of carbon annually, profoundly shaping the chemistry of our planet. Despite housing an estimated 10 billion tons of biomass, the mesopelagic zone remains one of the least understood ecosystems on Earth. The immense pressure, the near-freezing temperatures, and the absolute darkness create a frontier that pushes the limits of our technology. The organisms themselves are often so fragile, their gelatinous bodies dissolving in collection nets, that traditional sampling methods have offered only a fragmented glimpse of their true nature. This vast, hidden world, filled with life that glitters and drifts, continues to guard its secrets. Scientists are only beginning to grasp the sheer scale of its biodiversity, the intricate behaviors of its inhabitants, and the critical role it plays in the health of our planet. The twilight zone, silent and patient, awaits a deeper understanding that is only now starting to dawn. 1,000 meters below the surface, sunlight is a distant memory. The bathypelagic zone, known as the midnight zone, stretches from 1,000 to 4,000 meters in perpetual blackness. In this realm, evolution has abandoned pigment and eyesight in many creatures, while others have developed enormous, light-sensitive eyes to capture the faintest bioluminescent glow. Here, life is sculpted by the absence of light. The temperature holds steady between 2 and 4 degrees Celsius, a cold so unvarying that seasons lose all meaning. Pressure mounts to over 100 times that of the surface, collapsing any air-filled space. To survive, creatures of the midnight zone have become gelatinous, their bodies composed mostly of water and incompressible fluids. As dusk falls in the upper ocean, the deep scattering layer begins its nightly ascent. This vast, false bottom echo, detected by sonar, is the mass migration of countless lanternfish, siphonophores, and minuscule crustaceans rising from the twilight zone to feed under cover of darkness. By day, they retreat to the depths, carrying organic carbon deep into the bathypelagic realm, sustaining the life below. This vertical commute is the largest animal migration on Earth by biomass. Among the scavengers awaiting this downward rain of marine snow is the giant isopod, a creature that looks like a pill bug the size of a small dog. Growing up to 50 centimeters long, it is a textbook example of deep-sea gigantism, a phenomenon where animals grow larger than their shallow water relatives due to extreme cold, pressure, and scarce food. Giant isopods can survive for years without eating, their metabolism so slow that a single meal might sustain them for months. They scuttle across the sediment on 14 legs, sensing the chemical signature of a carcass that has fallen from above. Plunging into this world is the sperm whale, a mammal that holds its breath for over an hour to reach depths of 2,000 meters and beyond. Here, it hunts the giant squid, an elusive cephalopod with eyes the size of dinner plates, perfectly adapted to detect the faintest light in the darkness. The whale's body is built for the crushing pressure, its ribcage flexible and lungs collapsing to prevent nitrogen narcosis. The epic struggle between these two titans takes place in silence, a battle witnessed by no one. In the midnight zone, time stretches thin. The permanent darkness, the near-freezing temperatures, and the immense pressure have forged a realm of patient, slow-motion survival. Bioluminescent flashes punctuate the blackness, the only light this world will ever know. It is a place of quiet endurance, where every creature is a testament to life's ability to adapt to the most extreme corners of our planet. Right now, as you lie in the dark, countless creatures unknown to science are moving through the deep ocean's silent, lightless waters. Far below the sunlit surface, beyond the continental slopes, lies a realm of near absolute stillness. The abyssal plain begins where the seafloor stretches out into a vast flat expanse, covering more than half of the Earth's solid surface. At depths between 4,000 and 6,000 meters, the pressure is immense and the temperature hovers just above freezing. This is the largest single ecosystem on the planet, yet it remains one of the least explored. In this permanent darkness, life is sparse but tenacious. Sea cucumbers move slowly across the sediment, sifting through the ooze in search of organic particles. Polychaete worms burrow into the mud or wave feathery gills at the water, while giant single-celled xenophyophores sprawl across the seabed like fragile, branching structures of agglutinated sediment. Every creature here is adapted to an existence where energy is a rare and precious commodity. Almost all nourishment in the abyss descends from above, in a gentle, continuous shower known as marine snow. This is a slow drift of organic debris, fragments of dead plankton, fecal pellets, and other particles that have fallen from the productive surface waters. A single flake may take weeks or even months to complete its journey down through miles of ocean. By the time it settles on the abyssal plain, only a tiny fraction of the original organic matter remains, a meager ration for the deep-sea community. Life here moves at a pace that is almost geological. The extreme slowness of the abyss is governed by the scarcity of food, the cold, and the crushing pressure. A sea cucumber might take a minute to travel a few centimeters, and some deep-sea organisms have metabolic rates so low that they can survive for decades on a single meal. Reproduction is infrequent, growth is incremental, and lifespans can stretch to centuries, making the abyssal plain a world where time itself seems to dissolve. The sediment that blankets the plain accumulates at a rate of only a few millimeters every 1,000 years. This fine, mineral-rich mud, often reddish or brown, is a mixture of wind-blown dust, volcanic ash, and the microscopic remains of plankton that have dissolved in the deep water. Over millions of years, this slow rain of particles builds a layer of extraordinary consistency, a quiet archive of Earth's climate and oceanic history pressed into the seafloor. Across certain regions of the abyssal plain, the flat sediment is punctuated by fields of potato-sized nodules. These polymetallic nodules form over tens of millions of years, slowly accreting layers of manganese, nickel, and cobalt around a tiny core. They provide the only hard substrate for countless miles, and their surfaces host a unique ecosystem of sponges, soft corals, and foraminifera that would otherwise have no anchor in the soft mud. These nodule fields are oases of biodiversity in the immense, quiet desert, fragile communities that have grown grain by grain over eons. The Hadal zone begins where the abyssal plains end, at a depth of 6,000 meters, and plunges into the narrow, dark fissures known as ocean trenches. There are 37 confirmed Hadal trenches scattered across the planet, each a deep scar in the seafloor formed by the slow, violent collision of tectonic plates. These remote corridors are the least explored habitats on Earth, yet they are home to a surprising assembly of life. The deepest of them all is the Mariana Trench, and at its southern end lies the Challenger Deep, a depression that descends to 10,935 meters. The pressure here is over 1,000 times the atmospheric pressure at sea level, a crushing force that would instantly collapse any air-filled space. In this realm of perpetual darkness and near-freezing temperatures, life has taken forms so perfectly adapted that they seem to belong to another world. Marine biologist Alan Jameson and his team have revolutionized our understanding of these depths by deploying baited camera landers into multiple trenches. Their footage has revealed a bustling community of scavengers, most notably swarms of amphipods, translucent snailfish, and elongated sea cucumbers known as holothurians. These creatures gather around any morsel of organic matter that drifts down from the surface, their existence defying the long-held belief that the very deepest ocean was a lifeless void. One of the most celebrated discoveries was the filming of a snailfish at 7,966 meters in the Mariana Trench. This species, later named Pseudoliparis suirae, moves with a delicate, almost ethereal grace, its gelatinous body appearing like a ghostly tadpole in the abyssal gloom. It remains the deepest living fish ever recorded, hovering just below the theoretical limit at which fish proteins can function. To survive where pressure can reach 8 tons per square inch, Hadal organisms have evolved profound biochemical defenses. Their cells are saturated with organic osmolytes like trimethylamine N-oxide, which stabilizes proteins and prevents them from being distorted by the immense force. Many deep-sea fish also lack a swim bladder. While their bones are reduced, their tissues are dominated by water, and their enzymes are modified to remain flexible under conditions that would render surface proteins rigid and inert. In several Hadal trenches, particularly the Kermadec and the Peru Chile, scientists have observed a phenomenon known as Hadal gigantism. Amphipods, which are normally the size of a thumbnail in shallow waters, can reach the length of a human hand, with the species Alicella gigantea growing up to 34 centimeters. This dramatic increase in size may be a response to the extreme pressure, a slow metabolism, or a strategy to better locate scarce food in the vast darkness, and these giant crustaceans glide through the black water with a quiet, unexpected authority. In the permanent night of the abyssal plain, the last decade of exploration has rewritten our understanding of life on Earth. Vessels like Noé's Okeanos Explorer and the Schmidt Ocean Institute's Falkor have sent remotely operated vehicles into depths where sunlight never penetrates. Each descent is a slow drift through the water column, a quiet passage into a realm that remains less mapped than the surface of Mars. What these expeditions routinely bring back to the surface is a catalog of the unknown. On a typical deep-sea voyage, between 20 and 30% of the biological specimens collected are entirely new to science. The moment of discovery is hushed, a murmured observation in a control room bathed in the blue glow of monitors, as a creature never before seen by human eyes pauses in the camera's frame. Among the most graceful of these discoveries are new species of the Dumbo octopus, genus Grimpoteuthis. These finned cephalopods hover just above the sediment, their ear-like fins undulating with a slow, mesmerizing rhythm as they probe the ooze for small worms and crustaceans. They have been observed at depths exceeding 4,000 meters, a reminder that life in the deep ocean is not a desperate struggle, but a patient, elegant adaptation to immense pressure and cold. Higher in the twilight zone, the barrel-eye fish, Macropinna microstoma, has drifted from the pages of scientific journals into living, luminous reality. For decades, its transparent, shield-like head and tubular green eyes were known only from damaged trawl specimens. Only in recent years have high-definition cameras on deep-diving robots captured the fish undisturbed, revealing how it hovers motionless, its eyes rotating to gaze upward through the fluid-filled dome, scanning for the silhouettes of prey against the faint surface light. On the continental slopes, the expeditions have also illuminated ancient forests of glass. Glass sponge reefs, built by the siliceous skeletons of hexactinellid sponges, were long thought to have vanished in the Jurassic. Their living rediscovery off the coast of British Columbia was a profound shock, and subsequent NOAA and Schmidt ocean surveys have mapped vast, previously unknown reef complexes, their delicate lattices rising from the seafloor like submerged cities of spun glass. These reefs form a living substrate, offering shelter to rockfish, shrimp, and countless other organisms in a slow, centuries-long construction project. The cumulative result of these voyages is a quiet revelation. With every kilometer of seafloor transected, the baseline of our planet's biodiversity expands, and the sheer volume of unknown life becomes a soothing counterpoint to the mapped world above. As the ROVs surface and the ships cut their engines, the data streaming back to laboratories on land adds layer upon layer to a portrait of the deep that is only just beginning to take shape. A reminder that the most profound discoveries often lie waiting in the silent, patient dark. In the early years of this century, a sailing yacht named Sorcerer II traced a quiet path across the world's oceans. Her voyage, led by genomics pioneer Craig Venter, was not a search for visible wonders, but for the invisible multitude suspended in every drop of water. Between 2003 and 2010, the Global Ocean Sampling Expedition collected water samples from the North Atlantic to the Sargasso Sea, from the Pacific to the Southern Ocean. The mission was to read the ocean's genome, the collective DNA of its smallest inhabitants. This emerging field relied on environmental DNA, or eDNA, the genetic material shed by organisms into their surroundings. A single water sample contains a drifting library of fragments left behind by microbes, larvae, and larger creatures as they move and decay. By sequencing these fragments, scientists could identify species without ever seeing them, revealing a hidden census of life far richer than anything visible to the naked eye. What they found redefined the scale of life. A single liter of sunlit seawater, once thought relatively barren, was revealed to contain millions of microbial cells. Each cell is a living entity, a tiny vessel of genetic information, and together they form a vast, invisible forest of life. The numbers are so immense that a mere teaspoon of ocean holds a universe of genetic diversity, a cosmos too small to see yet teeming with activity. These microscopic beings are not merely passengers in the sea. They are the planet's silent lungs, producing roughly half of the oxygen we breathe. Through photosynthesis, cyanobacteria like Prochlorococcus and Synechococcus turn sunlight and carbon dioxide into organic matter, releasing oxygen as a byproduct. Every second breath we take, on average, comes from the ocean's microbial realm, a gentle planetary rhythm powered by the smallest of engines. The sequencing of ocean DNA also unveiled something deeply profound: entire phyla of life that had never been seen before. Metagenomic analysis, which pieces together genomes from the mixed genetic soup, revealed novel branches on the tree of life. These unknown phyla, sometimes called the microbial dark matter, had no cultivated representatives, no photograph, no name, only the ghostly presence of their genetic code. They were ancient lineages, surviving in the ocean's depths, their existence rewriting the story of life's diversity. The ocean genome remains only partially read, a vast and gentle murmur of information waiting to be deciphered. Each new expedition, each liter of water drawn from the sea, adds a few more letters to a narrative that has been unfolding for billions of years. The invisible life of the ocean, once hidden, now speaks to us in sequences of DNA, a quiet reminder that the most profound stories are often the ones we cannot see. In the deep, lightless plains of the abyss, the sudden arrival of a dead whale is a profound ecological event that can reshape the seafloor for generations. The significance of these leviathan carcasses, now known as whale falls, only came into focus in the late 1980s, when oceanographers exploring the Santa Catalina Basin in a submersible stumbled upon a skeleton bristling with life. It was a discovery that revealed a hidden stepping stone in the deep ocean, a concentrated pulse of organic matter that creates a point of refuge and dispersal in a vast, nutrient-starved desert. The first act of a whale fall unfolds with startling speed as the body settles on the silty plain. A frenzy of mobile scavengers drawn from great distances descends upon the carcass. Sleeper sharks, rat-tail fish, and dense swarms of hagfish use rasping tongues and toothed mouths to tear away the soft tissue, consuming up to 50 kilograms of blubber and muscle each day. This frenetic stage can strip a whale of its flesh in a matter of months, though for a large cetacean it may stretch for 2 years, leaving behind a skeleton on a carpet of nutrient-rich detritus. As the large scavengers depart, the whale fall enters a quieter second stage, dominated by a dense carpet of much smaller organisms known as enrichment opportunists. Polychaete worms, tiny crustaceans, and mollusks colonize the bones and the surrounding sediments, which are now saturated with organic particles and oils from the decomposing flesh. These animals, many of which are generalists capable of surviving organic enrichment anywhere, feed on residual tissue and the abundant bacterial mats that have bloomed for a few fleeting years. The third and most enduring stage is a silent, alchemical one, powered by the very bones of the whale. The skeleton is rich in lipids, and as seawater seeps into the marrow, a community of sulfophilic or sulfur-loving bacteria takes hold. These microbes breathe sulfate and break down the whale's bone oils, producing hydrogen sulfide as a byproduct, which in turn fuels a whole ecosystem of chemoautotrophic bacteria that use the sulfide to create energy, just as plants use sunlight. This stage constructs a self-contained oasis of bright white bacterial mats and dense clumps of tube worms that can persist for decades. It is here, within this sulfide-driven feast, that the true specialists of the whale fall reside, creatures that exist nowhere else on Earth. The most remarkable of these are the Osedax, a genus of polychaete worm whose name translates to bone devourer. Lacking a mouth and a gut, the female Osedax secretes a remarkable acid that dissolves the whale's hard bone matrix, exposing the fatty lipids within. Symbiotic bacteria living inside the worm's root-like tissues then digest these lipids, nourishing their host in a collaboration that allows the worm to burrow deep into the skeleton, its feathery red plumes swaying in the currents like a field of tiny, grotesque flowers. The lifespan of a whale fall is a slow, drawn-out exhalation, sustaining a succession of life for a period that can span a human lifetime or more. A massive whale carcass may fuel this deep-sea oasis for a century, with the sulfophilic stage alone lasting for over 50 years. This creates a chain of ephemeral habitats across the ocean floor, where specialists like the bone-eating worm and other endemic snails and limpets go through countless generations, dispersing larvae into the dark currents in a perpetual search for the next great, silent benediction from the surface world. The deep ocean remains our planet's largest, least explored wilderness, a realm where absolute darkness and crushing pressure conceal perhaps 3/4 of Earth's living species. This unknown is not a void, but a living library, holding answers to fundamental questions about the origin of life, the evolution of biodiversity, and the ocean's role in regulating climate. Every new expedition reveals that the seafloor is far more varied and dynamic than we imagined. From vast abyssal plains to forests of hydrothermal chimneys, and the significance of what remains hidden is that it may rewrite the very story of our living planet. The pace of discovery has quickened notably since 2010, a year that marked a turning point in global investment for deep-sea science. Governments, international bodies, and private philanthropists began directing unprecedented resources toward ocean exploration, spurred by the understanding that the deep sea is not a remote afterthought, but a critical engine of planetary health. The United Nations Decade of Ocean Science for Sustainable Development, launched in 2021, consolidated this momentum, channeling billions of dollars into coordinated research programs that promise to shrink the unknown faster than any previous era. A monumental expression of this ambition is the Nippon Foundation GEBCO Seabed 2030 project, a global effort to map the entire ocean floor by the end of this decade. When the project was announced in 2017, only 6% of the seafloor had been charted to modern standards. By 2024, that figure surpassed 25%, an exponential leap driven by the voluntary sharing of bathymetric data from hundreds of research vessels, commercial ships, and even recreational yachts. This crowdsourced mapping initiative is not merely a cartographic exercise. It provides the foundational three-dimensional canvas upon which all subsequent biological and geological discovery is painted, revealing the contours of seamounts, canyons, and trenches that shape entire ecosystems. New sensor technologies have transformed how we glimpse these hidden landscapes. A single autonomous underwater vehicle can now carry a suite of instruments that were once confined to a laboratory: environmental DNA samplers that capture the genetic fingerprints of passing organisms, multi-beam sonar that paints the seafloor in exquisite detail, and hyperspectral cameras that detect the faint chemical glows of thriving microbial mats. These intelligent robots, capable of months-long missions without human intervention, are effectively compressing decades of ship-based survey time into a single season, making the deep ocean accessible to continuous observation rather than isolated snapshots. The flood of imagery and data from these platforms would be overwhelming without a parallel revolution in how we analyze it. Through citizen science portals like Zooniverse, over 15,000 volunteers have trained their eyes on seafloor footage, annotating the outlines of sponges, corals, and elusive fish, and their collective classifications have built a vast training library for machine learning algorithms. These artificial intelligence systems now process thousands of hours of video from observatories like the Monterey Bay Aquarium Research Institute, identifying rare events and unknown organisms in real time, a symbiosis of human pattern recognition and machine speed that accelerates the cataloging of life from a trickle to a torrent. Looking ahead 2 decades, scientists anticipate revelations that will fundamentally reshape our understanding of the biosphere. They expect to discover entire metabolic pathways that rely on chemicals rather than sunlight, yielding novel enzymes for medicine and industry, and to find microbial communities that expand the known boundaries of temperature, pressure, and pH for life. The complete map of the seafloor will likely reveal a network of hydrothermal vent fields far more extensive than predicted, and the deep biosphere, a living layer within the crust, may prove to be the largest reservoir of biomass on the planet. In the quiet, patient way of the deep, what was once an empty expanse is steadily resolving into a vibrant, intricate cosmos, and the coming years promise to fill the darkness with the light of a new biology. In the deep darkness of the ocean, a vast mountain range snakes across the globe. The mid-ocean ridge is the longest mountain chain on Earth, stretching over 65,000 kilometers. Here, tectonic plates slowly pull apart, and molten rock rises from the mantle to create new ocean crust. This process, known as seafloor spreading, continuously adds fresh material to the ocean floor. Along the boundaries of the Pacific Ocean lies the Ring of Fire, a horseshoe-shaped belt of intense seismic and volcanic activity. Most of the world's volcanic eruptions occur here, many hidden beneath the waves. Underwater volcanoes release magma that cools rapidly into billowing pillows of basalt, building new seafloor features and occasionally breaching the surface to form volcanic islands. Scattered across the deep ocean basins are seamounts, extinct submarine volcanoes that rise at least 1,000 meters from the seafloor. Scientists estimate there are over 100,000 of these submerged mountains, yet fewer than 1% have been surveyed in any detail. Each seamount is a hidden peak, often harboring rich ecosystems of deep-sea corals and sponges that thrive on the nutrient-rich currents swirling around their slopes. Some of these mountains have surprisingly flat tops, as if their peaks were once sheared away. These are guyots, ancient volcanoes that once stood tall enough to emerge above the sea surface. Wave action eroded their summits over millennia, planing them into broad plateaus. As the ocean floor subsided and sea levels fluctuated, these truncated mountains sank back into the depths, preserving their distinctive tabletop shapes. The vast majority of the ocean floor is remarkably young in geological terms. Most of it is less than 200 million years old. whereas the ancient cores of continents can exceed 4 billion years in age. The constant creation of new crust at mid-ocean ridges and its eventual destruction elsewhere means the seafloor is a transient feature, continuously recycled while the continents drift slowly above. The engine of this recycling lies in subduction zones, where the denser oceanic plate bends and plunges back into the Earth's mantle. Trench systems like the Mariana Trench mark these deep-sea scars where the floor is pulled downward. As the plate descends, it transforms, melting and fueling volcanic arcs, completing a cycle that has been shaping the ocean basins for hundreds of millions of years. The ocean is the quiet engine of our climate, absorbing and redistributing heat on a scale that dwarfs every current of air. It has taken in more than 93% of the extra energy trapped by greenhouse gases since the dawn of the industrial era. Without this vast thermal buffer, the atmosphere would have warmed far more rapidly, and the land we live on would already be a much harsher place. This heat does not simply sit still. It is caught in a slow planetary loop known as thermohaline circulation, a global conveyor belt driven by tiny differences in temperature and salinity. Warm surface waters travel thousands of miles toward the poles, releasing heat into the air and moderating climates along the way. As they cool, their density increases, and they begin a long, silent journey into the deep. The Atlantic Meridional Overturning Circulation, or AMOC, is the most powerful branch of this conveyor, carrying immense volumes of warm tropical water northward. It is the reason winters in Western Europe are far milder than at similar latitudes across the Atlantic. The AMOC functions like a giant heat pump, releasing warmth equivalent to 1 million large power stations into the atmosphere above the North Atlantic. The pump relies on a precise mechanism of deep water formation, most famously in the seas between Greenland, Iceland, and Norway. Here, frigid Arctic winds strip heat from the surface, and the formation of sea ice leaves behind extremely cold, salty water. This dense water sinks rapidly, plunging more than 2 kilometers down to form the North Atlantic deep water, a current that then flows south along the ocean floor, pulling warmer surface water in behind it to complete the cycle. A similar process unfolds in the Southern Ocean around Antarctica, where katabatic winds hurtling off the ice sheet create the densest water on Earth. Antarctic bottom water spreads across the abyssal plains of the world's oceans, a creeping icy pulse that feeds the deepest limb of the global conveyor. Together, these polar sinking zones are the lungs of the deep ocean, ventilating the abyss with oxygen and nutrients on a journey that can take a single drop of water 1,000 years to complete. If the AMOC were to weaken significantly, the impacts would cascade through the climate system. Northern Europe could face colder winters and disrupted growing seasons, while the tropical rain belts might shift, altering monsoon patterns for billions of people. Sea levels along the eastern seaboard of the United States would rise disproportionately as the ocean's slope relaxed. The conveyor has undergone abrupt slowdowns in Earth's past, and understanding its behavior today is one of the most urgent tasks in climate science. Far below the sunlit surface, where the ocean floor stretches away in frigid darkness, a different kind of oasis thrives without any warmth at all. Cold seeps are places where chemical-rich fluids slowly escape from the seabed, carrying methane and hydrogen sulfide rather than volcanic heat. Unlike hydrothermal vents, which are born of molten rock and superheated water, these ecosystems are powered entirely by the cold chemistry of the deep Earth. The existence of cold seeps was entirely unknown until 1984, when a submersible descended into the Gulf of Mexico and came upon a startling sight. Scientists were exploring the base of the Florida escarpment at a depth of over 3,000 meters and found dense clusters of life where none was expected. The discovery revealed that lush communities of tube worms, mussels, and clams were flourishing in the icy darkness, sustained not by sunlight but by the chemical bounty seeping from the seafloor. The foundation of this hidden world often lies in a substance that seems almost impossible beneath the sea. Methane ice, or gas hydrate, forms when methane molecules become trapped inside a cage of frozen water at high pressure and low temperature. These icy white deposits, which resemble snow-covered rocks, slowly release methane as they dissociate, providing a steady fuel for the microscopic life that underpins the entire ecosystem. Around these seeps, life has assembled itself into a remarkable society of organisms adapted to chemical energy. Dense gardens of vestimentiferan tube worms extend their red plumes into the water, their bodies housing symbiotic bacteria that convert hydrogen sulfide into nourishment. Thick beds of mussels and clouds of tiny polychaete worms cover the sediments, each species playing a role in a food web that begins with microbes, not plants. What makes cold seeps truly extraordinary is their endurance across vast stretches of time. While hydrothermal vents can flicker out as volcanic activity shifts, a cold seep can persist for tens of thousands of years, the slow, reliable leakage of hydrocarbons creating a stable sanctuary. Individual tube worms in these communities can live for centuries, making them some of the longest-lived animals on the planet, all sustained by the Earth's quiet, chemical breath. These ecosystems, hidden beneath kilometers of water, remind us that life's resilience is written in chemistry as much as in sunlight. From the icy clathrates to the silent, swaying tube worms, cold seeps are a testament to the deep, patient rhythms of our planet. They offer a glimpse of a world where the pulse of life is driven not by fire, but by the slow, invisible seep of ancient carbon from the rocks below. In the open ocean, drifting silently through the twilight zone, lives a creature that challenges our very definition of an animal. A siphonophore is not a single organism, but a floating colony composed of countless specialized individuals called zooids. Each zooid is genetically identical, yet it performs a distinct task, such as swimming, feeding, or reproducing, and cannot survive alone. Together, these interconnected bodies function as one harmonious entity, a string of living modules that stretches the boundaries of biological individuality. The scale of these colonial beings can be almost impossible to comprehend. Among the largest is Praia dubia, a deep-sea siphonophore whose delicate, transparent body can reach lengths of 40 meters, surpassing even the blue whale. This giant drifts on unseen currents, its body a fragile ribbon of gelatinous tissue that can extend for over 100 feet, making it one of the longest animals on the planet. Most of its length is a nearly invisible curtain of stinging tentacles that trails below a row of swimming bells. To hunt, a siphonophore deploys a lethal strategy of passive entrapment. It hangs a vertical curtain of tentacles, each armed with millions of microscopic harpoon-like stinging cells called nematocysts. Any small crustacean or fish that brushes against this drifting wall of venom is instantly paralyzed and reeled up to the feeding zooids. This silent, weightless net can cover a vast area of the water column, turning the colony into a deadly, living drift net. The most familiar siphonophore is one that often washes ashore on sandy beaches, the Portuguese man-of-war. Its gas-filled blue float, or pneumatophore, sits above the water like a small sail, while its long, ribbon-like tentacles stream below, delivering a powerful sting to swimmers. This iconic creature is a perfect example of a siphonophore colony, where the float, the tentacles, and the reproductive structures are all individual zooids working together for the survival of the whole. The true elegance of deep-sea siphonophores was revealed in stunning detail by the Schmidt Ocean Institute in 2020. During an expedition off the coast of Western Australia, the remotely operated vehicle Sebastian encountered a giant spiral-shaped siphonophore, likely of the genus Apolemia. The footage showed a luminous, corkscrew filament of zooids twisting through the dark water, its outer ring of tentacles forming a delicate silvery helix. The sight of this enormous, otherworldly colony, hovering motionless in the abyss, captivated scientists and the public alike, offering a rare glimpse of a living wonder. These colonial organisms remind us that the deep sea still holds profound mysteries. Their quiet, drifting existence challenges our land-based notions of what it means to be an individual, a predator, or even an animal. In the soft glow of a submersible's lights, a siphonophore appears less like a creature and more like a living constellation, a community of selves suspended in the endless dark ocean. In the deep, pelagic darkness, where sunlight fades into a permanent midnight, lives a creature of legend slowly yielding to science. The giant squid, Architeuthis dux, is the longest invertebrate known to science. Mature females can reach a total length of up to 13 meters, a measurement that includes 2 long, slender feeding tentacles extending far beyond the 8 arms. Most of what we know comes from specimens washed ashore or hauled up as accidental bycatch, their soft, reddish bodies crumpled on a deck. A heavier and more muscular cousin haunts the freezing waters of the Southern Ocean. The colossal squid, Mesonicoteuthis hamiltoni, is built not just for length but for mass, with a thick mantle and a body studded with sharp, swiveling hooks. In 2007, a New Zealand longline vessel fishing for Antarctic toothfish in the Ross Sea hauled up an extraordinary specimen from a depth of over a kilometer. That animal, a female, weighed nearly half a ton and provided the first intact adult for detailed study, revealing a creature far more formidable than the giant squid. Survival in the lightless abyss has shaped the most extraordinary eyes in the animal kingdom. Both giant and colossal squid possess eyes that can measure up to 30 centimeters across, roughly the size of a dinner plate. These vast orbs, with pupils that can open wide, are thought to be an adaptation for detecting the faintest glimmers of bioluminescence or the subtle silhouette of a predator moving against the faint downwelling light from above. That predator is the sperm whale, the only animal known to hunt these giant cephalopods routinely. The evidence is written on the whales themselves in the form of circular sucker scars raked across their heads and bodies. Inside the stomachs of sperm whales, scientists have found countless indigestible squid beaks, the hard, chitinous remains that accumulate by the thousands, confirming that a great battle between titans plays out in the deep, hidden from human eyes. For centuries, the living animal was a ghost, known only from death. The immense pressure of the deep ocean, the vastness of their habitat, and the sheer difficulty of reaching their world have kept them secret. The deep sea is a realm of crushing darkness where a submersible's lights and noise likely startle and repel these highly sensitive animals, meaning a human observer is almost always far too intrusive to witness natural behavior. Even now, with the first fleeting video footage of a giant squid in its own realm, captured off Japan in 2012, the lives of these invertebrates remain largely a closed book. We do not know how they hunt, how they mate, or what their full range of behaviors might be. The deep ocean keeps its secrets patiently, and the giant and colossal squid remain, for now, the quiet, watchful custodians of a world we are only beginning to glimpse. During the Second World War, naval sonar operators scanning the oceans for enemy submarines noticed something puzzling. Their instruments showed a phantom bottom, a dense layer that rose toward the surface at night and sank back into the depths by day, as if the entire seafloor were breathing. This layer, soon named the deep scattering layer, reflected sound waves so strongly that it was initially mistaken for a shallow seabed confounding military charts. Oceanographers later discovered that the false bottom was not rock or sediment, but a living veil of animals. The sound pulses were bouncing off the gas-filled swim bladders of lanternfish, the tiny chitinous bodies of krill, and the delicate gelatinous colonies of siphonophores. Together, these creatures form a vast, dense community that scatters sonar signals back to the surface, hiding the true ocean floor far below. Every night, as darkness spreads across the ocean, the largest animal migration on Earth begins. Trillions of creatures, from fingernail-sized copepods to palm-length myctophid fish, rise from the mesopelagic twilight zone toward the surface. They ascend hundreds of meters through the water column, a great vertical tide of life that, in total biomass, outweighs any terrestrial migration by several orders of magnitude. This mass movement follows a precise circadian rhythm. At dusk, the animals swim upward to feed under the cover of darkness, sheltered from visual predators. They spend the night grazing on phytoplankton and smaller zooplankton near the surface. Then at dawn, they descend back into the dark, cold water where they remain during the day. The entire living layer pulses upward and downward in a twice-daily heartbeat. The migration does more than redistribute life. It actively shuttles carbon from the surface to the deep ocean. The animals consume carbon-rich plankton near the surface, then retreat to depth, where they respire carbon dioxide and release dense fecal pellets that sink rapidly. This continuous downward flux of organic material, known as the biological carbon pump, locks atmospheric carbon away in the deep sea for centuries or millennia. Although invisible to the human eye, the deep scattering layer is one of the planet's most profound biological rhythms. Its nightly journey connects the sunlit surface world with the vast, dark interior of the ocean, sustaining deep-sea food webs and regulating global climate. Without this silent, ceaseless migration, the ocean's capacity to absorb and store carbon would be drastically diminished. In the crushing darkness of the deep ocean, pressures exceed 1,000 atmospheres, a realm where most life would be obliterated. Yet certain bacteria, known as piezophiles, do not merely endure this force, they require it. These organisms have woven pressure into the very fabric of their biochemistry, and if brought to the surface, their membranes rupture and metabolic processes seize, proving fatal within hours. While pressure shapes life in the abyss, temperature presents another relentless boundary. Much of the deep ocean hovers between 1 and 4 degrees Celsius, a near freezing constancy. Psychrophilic microbes thrive in this cold by producing enzymes that remain flexible and catalytically efficient at temperatures that would lock other proteins into rigid inactivity. Their cell membranes are rich in unsaturated fatty acids, maintaining fluidity like oil that refuses to solidify in the chill. In the very deepest trenches, such as the Mariana Trench, the microbial world shifts toward the archaea. These barophilic archaea are pressure-loving extremophils that dominate the sediment communities at depths beyond 10,000 meters. Species like Pyrococcus yainosi have been isolated from hydrothermal vents under extreme hydrostatic pressure, their cellular machinery optimized to function where the weight of the water column is almost beyond comprehension. Some of these archaea also exhibit hyperthermophilic traits, revealing a dual adaptation to both crushing pressure and scalding heat. To survive such depths, many deep-sea organisms, from fish to microbes, employ a small organic molecule called trimethylamine oxide, or TMAO. This compound acts as a chemical chaperone, stabilizing proteins by strengthening the hydrogen bonding network of water and preventing the collapse of protein structures under pressure. TMAO effectively counteracts the pressure-induced distortion of enzymes, allowing metabolic reactions to proceed smoothly. Its presence is so vital that the concentration of TMAO in tissues increases with the depth at which a species lives. The discovery of vibrant ecosystems in the deep ocean, powered not by sunlight but by chemosynthesis, has rewritten the rules of where life can exist. These extremophiles prove that the fundamental requirements for life are liquid water, an energy source, and a suitable chemical environment, not necessarily a sunlit surface. The icy moons of our solar system, such as Europa and Enceladus, are now thought to harbor deep liquid oceans under their frozen crusts, where hydrothermal vents might sustain life in conditions astonishingly similar to those in Earth's abyssal plains. This redefines the traditional concept of a habitable zone, the narrow orbital band around a star where surface water can remain liquid. The deep ocean teaches us that habitable zones can be far more extensive, stretching deep into the interiors of planets and moons where tidal heating or radioactive decay can maintain liquid water far from any stellar warmth. Life's tenacity at the edge of what is possible suggests that the universe may be far more alive than we ever imagined, hidden beneath layers of ice and rock in the quiet, patient dark. In the ocean, light fades quickly, but sound reigns supreme. A whisper can travel vast distances because sound moves roughly 4 times faster in water than in air. This is due to the close packing of water molecules, which transmit vibrations with far greater efficiency than the loose and springy air. At a depth of around 1,000 meters, a remarkable acoustic phenomenon occurs. Here, a combination of falling temperature and rising pressure creates a layer where sound speed is at its minimum. This is the SOFAR channel, a natural waveguide that traps sound waves, bending them back toward the center and allowing them to travel for thousands of kilometers with very little loss of energy. During the Cold War, the United States Navy built a secret network of underwater microphones called SOSUS, the Sound Surveillance System. Its purpose was to track the quiet movements of Soviet submarines across the North Atlantic and Pacific. When the Cold War ended, this vast array of hydrophones was gradually declassified and opened to the scientific community. Scientists suddenly had ears capable of listening to an entire ocean basin. They used SOSUS to monitor underwater volcanic eruptions, pinpoint the exact location of distant earthquakes, and track the haunting songs of great whales. The system revealed a hidden world of sound, where the low-frequency calls of fin and blue whales could be detected from one side of an ocean to the other. The great baleen whales are masters of this acoustic realm. Their deep, rumbling calls, some as low as 10 hertz, are perfectly tuned to the SOFAR channel. A blue whale's song can travel thousands of kilometers, allowing individuals to communicate across entire ocean basins. This is how the largest animals on Earth find each other in the vast, dark expanse. Today, the ocean's soundscape is a delicate balance of natural rhythms and human intrusion. The SOFAR channel, once a silent highway for whale song, now carries the relentless drone of shipping traffic. Yet in the quietest moments, the deep still echoes with the ancient calls of leviathans, a reminder that sound is the very heartbeat of the ocean. In the vast and lightless depths of the ocean, sound travels great distances through a medium that is largely invisible to us. For decades, the deep sea has yielded recordings that defy immediate explanation, snippets of acoustic intrigue captured by submerged listening devices. Among the most famous of these is a sound that was detected in 1997 by hydrophones across the Pacific Ocean, a noise so immensely powerful it was picked up by sensors over 5,000 kilometers apart. It was nicknamed the bloop, a rising, ultra-low frequency groan that, for a time, appeared to be the signature of a creature far larger than any known whale. Years later, after careful analysis of its acoustic profile, scientists linked the bloop not to a living giant, but to the shuddering basso profundo of massive ice quakes, the cracking and fracturing of icebergs far from any human ear. That same year, the network of NOAA hydrophones registered another peculiar sound analysts called the slowdown. This signal descended in frequency over approximately 7 minutes, a long, sighing glissando that sounded almost like air being released from a vast balloon. Its source was traced to the remote equatorial Pacific, and its gradual downward sweep hinted at a large, decelerating object. The leading theory now points to the grounding or friction of a colossal iceberg grinding against the seafloor, an event that transforms kinetic energy into a mournful, drawn-out acoustic signature. The ocean's repertoire of unexplained sounds from the late 1990s also includes a mechanical drone named Train and a pure, eerie tone called Whistle. Train, recorded in the Pacific, rose steadily in frequency, mimicking the sound of a distant locomotive horn filtering through the water. Whistle, captured on July 7, 1997, resembled a single, clean note, closer to the vocalization of a synthetic creature than any known marine animal. Both of these sounds, while initially puzzling, are now thought to be connected to the restless movement of ice, with the Train signature possibly caused by a berg scraping along an irregular coastline or volcanic tremor, and the whistle linked to the resonant vibration of ice as it cracks under pressure. Then there is Julia, a sound of uncertain origin that remains one of the more haunting moments in the archive of deep-sea listening. Recorded on March 1, 1999, by the Autonomous Hydrophone Array in the Equatorial Pacific, Julia lasted roughly 15 seconds and resembled a wavering, cooing call, almost conversational in its timbre. Its spectral signature was distinctive enough to rule out a submarine or a standard seismic event, yet it did not match any known biological source. The most plausible explanation places Julia among the sounds of a massive iceberg, perhaps one that was calving or dragging along the seabed. Yet the precise mechanics behind its strange, amiable quality remain a subject of quiet scientific curiosity. These recordings were made possible by a network of hydrophones originally designed for a very different purpose during the Cold War: the Sound Surveillance System, or SOSUS, which was built to track Soviet submarines. After the end of the Cold War, the United States Navy allowed parts of this classified network to be used for civilian scientific research, opening an unprecedented window into the acoustic life of the global ocean. The unexplained sounds of the 1990s were not anomalies but the first hints of a rich and complex soundscape, an introduction to the planet's own hidden voice, where the groan of ice, the tremor of the seafloor, and the calls of whales all blended into a continuous, low-frequency symphony. Today, the global ocean is passively monitored around the clock by a federation of hydrophone arrays, including the International Monitoring System of the Comprehensive Nuclear Test Ban Treaty Organization and dedicated scientific networks. These systems listen not with active sonar, but with silent, patient receivers that capture the ambient pulse of the planet, from the song of a blue whale in the Indian Ocean to the distant rumble of a submarine volcanic eruption. The sounds that once seemed so mysterious, including the bloop, the slowdown, and Julia, have taught us that the deep is not a silent void, but a resonant chamber, where the movements of ice, earth, and life itself compose a never-ending and deeply informative narrative. In the sunlit upper reaches of the ocean, a silent forest of microscopic algae called phytoplankton drifts with the currents. These tiny organisms perform a quiet miracle, capturing dissolved carbon dioxide and using the energy of the sun to transform it into organic matter through photosynthesis. Every breath we take is tied to this process, which generates roughly half of the oxygen in our atmosphere. The carbon they fix becomes the foundation of the marine food web, a fleeting store of energy in the surface waters. When phytoplankton cells die or are consumed, their remains begin a long journey into the abyss. Fragments of cells, discarded feeding nets, and other organic debris clump together into delicate, snow-like particles known as marine snow. This continuous shower drifts downward at a pace of a few hundred meters per day, carrying the carbon of the surface into the twilight zone and beyond. Much of it is recycled by microbes on the way down, but a resilient fraction settles into the deep ocean, where it is isolated from the atmosphere for centuries. Zooplankton, the tiny animals that graze on phytoplankton, serve as the couriers of this carbon transport system. Creatures like copepods and krill ingest the microscopic algae and package the indigestible material into dense, membrane-bound fecal pellets. These pellets sink far faster than loose marine snow, sometimes reaching speeds of hundreds of meters per day, effectively injecting carbon into the deep sea. It is a biological shortcut, a rapid transit line that bypasses the slow drift of individual particles. Each year, this biological pump draws an estimated 5 to 12 gigatons of carbon from the surface ocean into the interior. To put that number in perspective, it is comparable to the total annual carbon dioxide emissions from all human activities. Without this silent planetary scale sequestration, the concentration of carbon dioxide in our atmosphere would be significantly higher. The pump is not a constant, however. It pulses with the seasons and the rhythms of ocean life, a vast breathing system hidden beneath the waves. This process is a critical stabilizer of Earth's climate, acting as a natural thermostat over geological timescales. By locking carbon away in the deep ocean, it prevents it from returning to the atmosphere as a greenhouse gas, keeping our planet habitable. The cold, dark waters of the deep sea hold this carbon for hundreds to thousands of years, a reservoir so immense that it dwarfs the carbon stored in the terrestrial biosphere. In this way, the ocean's depths are the final resting place for much of the carbon that enters the marine realm. A warming world, however, is beginning to slow this vital machinery. Rising surface temperatures strengthen the stratification of the ocean, making it harder for deep, nutrient-rich waters to rise and replenish the sunlit zone. This can starve phytoplankton, shifting communities towards smaller species that are less efficient at exporting carbon. As the biological pump weakens, the ocean's capacity to absorb our excess carbon dioxide diminishes, creating a feedback loop that could accelerate climate change in the decades to come. In the deep, cold waters off the coast of British Columbia, a discovery in the 1980s rewrote our understanding of the living seafloor. Scientists using sonar to map the continental shelf detected vast, jagged mounds rising from the depths, structures that should not have been there. Descending in submersibles, they found themselves gliding over a silent metropolis of glass, a reef system built not by coral, but by living creatures of pure silica. This was a glass sponge reef, a sprawling complex that would soon be compared to the Great Barrier Reef in its scale and ecological significance. The architects of these submerged citadels are hexactinellids, or glass sponges, whose bodies are woven from a lattice of microscopic silica spicules. Each sponge is a living filter, drawing in the surrounding seawater through tiny pores and expelling it through a central cavity. A single, modestly sized specimen can process hundreds of liters of water every day, sieving out bacteria and plankton with quiet efficiency. Entire reef formations, with millions of individuals, cleanse staggering volumes of the ocean, shaping the chemistry and clarity of their deep-water realm. For paleontologists, the shape of these reefs was hauntingly familiar. The fossil record holds immense glass sponge reefs dating back to the Jurassic period, when they stretched across the ancient seafloor of what is now Europe in great glittering ridges. These prehistoric structures, formed by a symbiotic partnership between sponges and silica-secreting bacteria, left behind massive limestone and chert deposits that can be traced for hundreds of kilometers. They were a dominant feature of the Mesozoic Ocean, a forgotten architecture of the deep past. The scientific consensus had long held that these reef-building glass sponges had vanished from the Earth around 40 million years ago, snuffed out by changing conditions at the end of the Eocene. Their existence was confined to textbooks, a vanished world known only from the stony ghosts entombed in cliffs and quarries. The notion that a living, breathing example could still exist, hidden in the depths of the Pacific, was simply beyond the imagination of marine biology. The 1980s discovery therefore felt less like a new find and more like a message from the geology of another age. These ancient reefs are not monuments to the past alone. They serve as vital nurseries and sanctuaries for a host of deep-water species, their intricate three-dimensional framework providing refuge in the otherwise soft, muddy plains of the continental slope. Juvenile rockfish, slow-growing and vulnerable, find shelter within the delicate glass thickets, while clouds of spot prawns and other crustaceans hover above the sponge gardens. The reefs concentrate life, creating vibrant oases of biodiversity that are critical to the health of the entire region. To drift in a submersible across a glass sponge reef is to witness a living fossil, a Jurassic seascape that has somehow persisted into the modern world. The sponges grow with an almost geological slowness, their glassy skeletons accumulating layer upon layer over centuries. In the absolute darkness, they filter the sea with a patience that defies human timescales, sustaining a quiet and ancient community that we have only just begun to observe. Their rediscovery is a profound reminder that the deep ocean still holds secrets capable of reshaping our understanding of life on Earth. In the heart of the western Pacific Ocean, the Mariana Trench descends into a darkness that is almost absolute. The first human eyes to witness this realm belong to Lieutenant Don Walsh and Swiss engineer Jacques Piccard, who on January 23, 1960, piloted the bathyscaphe Trieste to the bottom of the Challenger Deep. Through a small porthole, they glimpsed a flatfish-like creature, a sight that proved life could endure under pressures exceeding 1,000 atmospheres. Their stay lasted only 20 minutes, but it marked the beginning of humanity's quest to understand the deepest place on Earth. More than half a century later, in March 2012, filmmaker and explorer James Cameron descended alone in the submersible deep-sea Challenger, becoming the first person to reach the trench solo. His custom-built craft, painted a vivid green, took over 2 hours to fall through the water column. At the bottom, Cameron observed a surprisingly barren landscape of fine sediment, but his cameras captured the faint movements of small shrimp-like creatures and the telltale signs of microbial life. He spent several hours collecting samples and footage before a slow, deliberate ascent. The most comprehensive survey of the trench came with the Five Deeps expedition, led by American explorer Victor Vescovo, between 2018 and 2019. Vescovo's submersible, the limiting factor, reached a verified depth of 10,128 meters in the Challenger Deep, setting a new record for the deepest solo dive. During multiple descents, the expedition mapped the trench floor with unprecedented precision, revealing rocky outcrops, soft sediment plains, and even a small undersea hill. The data collected reshaped scientific understanding of the trench's geography and its extreme environment. Yet even at such depths, evidence of human activity has been found. In 2019, Vescovo's team observed a plastic bag and candy wrappers lying on the seabed, a stark reminder that pollution reaches every corner of the planet. Marine biologists later confirmed that the polymer debris had been carried by deep currents, degraded by pressure, but not destroyed. The discovery underscored the fact that the ocean's deepest trenches are not isolated from the surface world, but are instead final repositories for our waste. Despite the crushing pressure and eternal cold, life persists in remarkable forms. The snailfish, a translucent tadpole-like creature, has been filmed gliding along the bottom, its body adapted to withstand forces that would collapse most organisms. Amphipods, tiny crustaceans that resemble shrimp, swarm in enormous numbers, scavenging any organic matter that falls from above. Sea cucumbers, their bodies soft and gelatinous, creep across the sediment, feeding on the thin film of bacteria that coats the trench floor. Each expedition brings back new questions as well as answers. The Mariana Trench remains a place of profound isolation, where the pressure is equivalent to the weight of a small car pressing on every square inch. Scientists continue to study the organisms that thrive there, hoping to unlock secrets of adaptation and survival that may one day inform medicine and materials science. The deepest place on Earth, it seems, is far from silent or empty. It is a living archive of the planet's history and its future. The deep ocean remains our planet's largest unexplored habitat, a realm of crushing pressure and absolute darkness where every expedition can still rewrite the textbooks. In the coming decades, a quiet revolution in technology will part the veil on this hidden world, not with a single dramatic plunge, but through a sustained, networked effort of mapping, listening, and sampling. The coming generation of explorers will be robotic, intelligent, and endlessly patient, allowing us to see the seafloor with a clarity once unimaginable. Central to this ambition is the Seabed 2030 project, a collaborative global effort to compile a complete bathymetric map of the entire ocean floor by the year 2030. Currently, only a fraction of the seabed is charted at high resolution, leaving vast abyssal plains and uncharted seamounts in the dark. Using a fleet of survey vessels and autonomous platforms equipped with multi-beam sonar, the project aims to stitch together a continuous mosaic, revealing the precise contours of every ridge, trench, and canyon that shapes our planet's surface. As remotely operated vehicles descend, they are now being paired with artificial intelligence that can recognize life in the drifting particles of the deep. AI-assisted species identification is moving beyond the slow, frame-by-frame analysis done by human eyes, allowing computers to instantly tag and count organisms from millions of hours of archived footage. This machine learning can be trained to spot the subtle flick of a bioluminescent jellyfish or the rare scuttle of a deep-sea amphipod, transforming our ability to measure biodiversity across entire ocean basins in real time. The eyes of the fleet will be countless autonomous underwater vehicles, gliding silently through the water column on missions spanning thousands of square kilometers. Free from the tether of a surface ship, these AUVs can descend to pre-programmed depths and follow the topography of the seafloor for months, methodically surveying mineral-rich nodule fields, investigating hydrothermal vent systems, and monitoring the quiet hum of biological activity. Their endurance allows them to reach places no crewed vessel ever could, such as the cavity beneath an ice shelf or the deepest, most fragile trenches, returning with a continuous stream of data and imagery. A different kind of search is conducted by simply sifting the water itself. Environmental DNA sampling allows scientists to collect the invisible genetic fingerprint left behind by every passing organism, from microbes to giant squid. A single liter of frigid deep water, filtered through a fine membrane, can contain a library of unknown life, revealing the presence of species that have never been photographed or collected. This technique is already detecting cryptic communities in the vast midwater realm and hinting at the true scale of biodiversity in the ocean's twilight zone. A genetic inventory of the sea without disturbing a single creature. The same logic of exploration that guides us in the abyss is now turning its gaze outward, toward the ice-covered moons of our solar system. The discovery of chemosynthetic ecosystems on Earth, where life thrives on chemical energy from hydrothermal vents rather than sunlight, provides a blueprint for what might exist beneath the frozen crust of Jupiter's moon Europa. If a global ocean, kept liquid by tidal heating, vents onto a rocky seafloor in the darkness, the coming decades of ocean exploration technology, refined in our own deep sea, will be our direct precursor to missions that melt through alien ice and search for the first signs of life beyond Earth. Far beneath the sunlit surface, where the ocean transitions from shimmering blue to an inkier shade, a curious phenomenon unfolds. Between roughly 200 and 1,000 meters, oxygen levels plummet, creating vast shadows in the sea known as oxygen minimum zones. These zones form where the slow decay of organic snow sinking from above consumes dissolved oxygen faster than sluggish currents can replenish it. The layered, stable waters of the open ocean prevent mixing, and what remains is a thin solution of seawater that challenges the very definition of breathable. Off the western coast of South America, one of the most intense oxygen minimum zones on Earth stretches beneath the Humboldt Current. This cold, nutrient-rich current fuels a spectacular bloom of life at the surface, yet the sheer volume of sinking organic matter from that abundance creates a deep sink for oxygen. The resulting tongue of hypoxic water is a permanent feature, a realm where oxygen concentrations can fall to less than 1% of surface values. It is a landscape of apparent absence, yet it is not empty. In this near-zero oxygen world, some creatures have rewritten the rules of survival. The Humboldt squid, a meter-long predator of the twilight zone, slows its metabolism dramatically and uses an exceptionally efficient blood pigment to bind what little oxygen is available. Certain fish, like the cusk eel, have enlarged gill surfaces and a heart that can function on a trickle of oxygen, allowing them to hunt in water that would quickly asphyxiate most other vertebrates. They move through the gloom with a slow, deliberate economy, living proof that the edge of physiological limits can be a niche. Today, these ancient boundaries are shifting. Ocean warming, driven by a changing climate, exerts a double pressure on the world's oxygen minimum zones. Warmer water holds less dissolved gas, and a more stratified surface layer makes it harder for oxygen to be mixed down from the atmosphere. As a result, the low oxygen shadows are expanding both vertically and horizontally, thickening the difficult middle layers of the sea and spreading into new regions. The slow creep of deoxygenation is quietly reorganizing deep-sea communities. Mobile, oxygen-hungry predators like certain tunas and sharks find their vertical habitat compressed, forced into ever shallower realms, while hypoxia-tolerant organisms like jellyfish and certain squid may extend their range. On the seafloor, the change can be even more profound, as the slow-growing oxygen-dependent communities of sponges and brittle stars give way to a simpler, hardier assemblage of polychaete worms and bacteria. The architecture of life in the deep is being redrawn. These hidden midwater plains, where breath itself is a scarce resource, remind us that the ocean's vastness holds many delicate thresholds. The creatures that dwell there have evolved an extraordinary tolerance over millions of years, yet the pace of change now tests even their remarkable adaptations. Silent and far from shore, the expansion of the oxygen minimum zones represents one of the most profound and least visible rearrangements of life on our planet. In the deepest reaches of the ocean, where sunlight never penetrates and the seafloor lies under crushing pressure, a quiet miracle of geology unfolds at a pace almost impossible to comprehend. Scattered across the sediment like a scattering of dark, misshapen potatoes, polymetallic nodules grow 1 millimeter every century. Layer by layer, they accrete metals precipitated from seawater and pore waters, slowly gathering manganese, nickel, cobalt, and copper around a tiny core such as a shark tooth or a fragment of basalt. It takes millions of years for a single nodule to reach the size of a human fist. Nowhere on Earth are these formations more abundant than in the Clarion-Clipperton Zone, a vast stretch of the Pacific Ocean between Hawaii and Mexico. Spanning over 5 million square kilometers, this abyssal plain is a mosaic of soft mud and rolling hills, where the nodules lie so densely in places that the seafloor resembles a cobbled path. The zone represents the largest known untapped reserve of these metals, a treasure chest assembled by the slow pulse of the Earth's chemistry across entire geological epochs. Far from being a barren wasteland, each nodule acts as a tiny island of solid substrate in a world of shifting silt. Glass sponges with delicate lattice-like skeletons anchor themselves to the metal crusts, while feathery-armed crinoids and brittle stars coil around them. Peering closer, a single nodule can host a microcosm of life. Translucent sea anemones, foraminifera encrusting the surface, and tiny crustaceans hiding in crevices. The surrounding sediment, too, is stitched with the burrows of polychaete worms, sea cucumbers, and xenophyophores, giant single-celled organisms that build fragile tests from the ooze. The same metals that make the nodules so valuable to modern technology have drawn the attention of mining companies and national governments. Proposals for deep-sea mining envisage fleets of remotely operated vehicles sweeping across the abyssal plains, vacuuming nodules from the seabed and pumping them to a surface vessel. The International Seabed Authority has issued exploration contracts for large sectors of the Clarion-Clipperton Zone, driven by the rising demand for battery metals in the green energy transition. The idea promises a supply of cobalt, nickel, and manganese without the social and environmental footprint of terrestrial mines. A growing chorus of marine scientists, however, has raised urgent concerns about what would be lost before we even understand it. Expeditions to the zone continue to reveal species new to science, with some estimates suggesting that over 90% of the animals collected are undescribed. The disturbance would not be limited to the nodules themselves. Sediment plumes generated by mining vehicles could travel vast distances, smothering filter feeders and disrupting the delicate chemistry of the abyssal waters. The very nature of this ecosystem, built on isolation and stability, makes it uniquely vulnerable to physical disruption. The tragedy of nodule mining lies in the irreversibility of the damage. Once removed, the nodules will not return for many millions of years, and the species that depend on their hard surfaces will have no foundation on which to recolonize. The animals of the abyss live with an extraordinarily slow metabolism, growing and reproducing at a rate that makes even the nodule growth seem rapid. In an environment that has remained essentially unchanged for millennia, a single pass of a mining collector would reset the ecological clock, leaving behind a landscape stripped of its complexity for human lifetimes beyond counting. The silence of the abyssal plain, once broken, would never truly return. In the deep ocean, Sunlight never penetrates. This perpetual night is a realm where the midnight sun has never been glimpsed, and the only glimmers come from the creatures themselves. To survive and reproduce in this vast darkness, animals have evolved an array of extraordinary senses that do not rely on light. Deep-sea fish read the water around them through a delicate sensory ribbon known as the lateral line. Microscopic hair cells embedded in this canal detect the faintest pressure waves, from the approach of a predator to the subtle movements of a potential mate. In the dark, a fish can feel the displacement of water caused by another's swimming, building a three-dimensional map of its immediate surroundings. Sharks and skates, ancient denizens of the deep, perceive the world through electricity. Networks of jelly-filled pores called ampullae of Lorenzini cluster around their snouts, sensing the minuscule bioelectric fields emitted by the muscle contractions of hidden prey. A flat fish buried in the sediment, invisible to the eye, becomes a beacon of electrical signals that a passing skate can detect with precision. Across the immense, lightless distances, scent becomes a lifeline. Many deep-sea animals release pheromones, chemical signatures that drift with the slow, deep currents. A male copepod or a tiny anglerfish can track a female's plume of pheromones for kilometers, following a molecular trail that grows stronger as he approaches. In this way, the ocean itself becomes a medium for chemical communication, guiding individuals through the abyss toward a mate. When two creatures finally meet, light often confirms their identity. Bioluminescence is the common language of the deep, and each species writes its own luminous script. A male lanternfish recognizes the specific pattern of photophores on a female's belly, while a female dragonfish signals with a glowing barbell in a precise rhythm. These living lanterns ensure that a potential mate is not mistaken for a predator, using flashes and glows as a species-specific code. In some lineages, the darkness has rendered eyes obsolete. Over evolutionary time, species like the blind cusk eel have abandoned vision entirely, their eye sockets now covered by skin or scales. Energy once spent on maintaining useless eyes is redirected to other senses, such as smell or mechanoreception, sharpening the tools that truly matter in a world without light. Their existence is a quiet testament to the relentless economy of natural selection. Months before a research vessel can set sail, the expedition begins as a slow accumulation of permit applications, safety protocols, and finely tuned logistical correspondence. Principal investigators map the seafloor with multi-beam sonar data from previous surveys, identifying hydrothermal vent fields, cold seeps, or abyssal plains that promise novel biology. They then submit detailed proposals to national funding agencies, justifying the scientific return of every hour at sea, while shore-based coordinators secure air freight for remotely operated vehicle components and hazardous material clearances for chemical preservatives. Once the cruise is funded and the ship's timetable is locked, the team turns to the dive schedule, a document that charts every meter of the seafloor the ROV will visit. Working from bathymetric charts and habitat maps, scientists assign each transect a priority ranking and build in contingency time for weather, equipment failure, or a discovery that demands an extra day of sampling. The ROV's manipulator arm and suction sampler are tested in a shoreside tank, and biologists pre-label hundreds of sample jars, each coded for a specific depth, temperature, and chemical regime. At sea, the ship operates on a relentless 24-hour rhythm, and the science party splits into two watches, typically covering noon to midnight and midnight to noon. When the ROV touches down, the on-watch team crowds the control van, directing the pilot toward bacterial mats or rock chimneys, while the off-watch crew sleeps in darkened cabins, knowing their turn will come just as the previous shift's samples are being processed. This rotation ensures that fragile specimens are never left unattended and that every dive produces a continuous stream of video annotations, physical measurements, and tissue samples. The moment a deep-sea organism is collected in an insulated sampling box, it begins a violent transition from a world of crushing pressure and near-freezing temperatures to one of bright light and rapidly warming air. At a depth of 2,000 meters, the pressure exceeds 200 atmospheres, and the cold, often around 2 degrees Celsius, keeps enzymes sluggish and cell membranes tightly ordered. As the ROV ascends through the water column, the ambient pressure drops by a factor of 200, allowing dissolved gases to expand and form bubbles in tissues, while the temperature climbs over a dozen degrees in less than an hour. Even with the most gentle ascent rates and chilled, Pressure-retaining vessels. The vast majority of deep-sea organisms arrive at the surface dead or suffering irreversible damage. Gelatinous creatures such as sactenophores and pelagic holothurians can partially disintegrate during the journey, their mesoglia rendered into a cloud of mucus by thermal shock alone. Fishes with swim bladders suffer catastrophic barotrauma as the gas expands, forcing the stomach to protrude through the mouth, while the delicate gill structures of vent shrimp collapse when the pressure drops below the threshold that keeps their enzymes functional. Because a living, intact specimen is so rare, every fragment of tissue, every partial genome, and every still frame of video becomes a hard-won prize. The scientists work quickly to photograph the animal in a chilled seawater bath, snip a tissue sample into liquid nitrogen for later DNA analysis, and preserve the remains in ethanol or formalin before decay erases the evidence. In this quiet, fluorescent-lit lab aboard a rolling ship, the effort to understand a hidden world continues, one careful record at a time. In the crushing darkness of the abyssal plain, where sunlight never reaches, a single remotely operated vehicle can record over 100 hours of high-definition video during a single expedition. The task of watching every frame, of cataloging every creature that drifts or scurries past the camera, would take a team of experts years. This is where the SciVid program steps in, a collaboration that invites volunteer citizen scientists to review this footage from their own homes. These volunteers, thousands of them, watch the slow, silent dances of the deep, clicking to mark the presence of a jellyfish, a squid, or a sea cucumber, turning raw video into a rich data set. Yet the volume of data is so immense that human eyes alone cannot keep pace. So machine learning models are trained on the very annotations that the volunteers provide. The models learn to recognize the subtle shapes and movements of deep-sea species, from the coiled tentacles of a siphonophore to the rigid armor of a crustacean. Over time, the algorithm becomes faster and more accurate, able to scan a video feed and flag a known species in a fraction of a second. The Zooniverse platform serves as the digital meeting ground for this work. Citizen scientists log in to a dedicated interface, often called a project page, where they are shown short clips of ROV footage. They are asked simple questions. Does this frame contain a living organism, and if so, what type? The answers are compiled into a database that becomes the foundation for both scientific discovery and the training of artificial intelligence. Zooniverse has hosted numerous deep-sea projects, allowing anyone with an internet connection to contribute to the exploration of the ocean floor. The speed of species identification has been transformed by this partnership. What once required a specialist to spend months examining a single dive can now be accomplished in days or even hours. The AI models, fed by the steady stream of human-verified data, can quickly process entire expeditions, identifying and counting organisms with a consistency that is difficult for any one person to maintain. The increase in speed is measured in orders of magnitude, turning a bottleneck into a floodgate of information. This relentless review of footage, powered by both human patience and machine efficiency, has led to the discovery of new behaviors. A species of deep-sea jellyfish, once thought to be a passive drifter, was observed repeatedly extending and retracting its tentacles in a pattern that suggested active hunting. A slow-moving sea cucumber was filmed releasing a cloud of bioluminescent particles, a behavior that had never been recorded. These moments, missed by a tired eye but caught by a systematic scan of thousands of hours, reveal a dynamic and surprising world in the depths. The deep ocean remains the largest and least explored habitat on Earth. Through the quiet collaboration of citizen scientists and machine learning, a clearer picture is emerging. The volunteers, often working in their spare time, and the algorithms, learning from every click, together form a new kind of explorer. They do not descend in a submersible. They watch, they annotate, and they teach the machines. And the deep ocean, reluctantly, begins to share its secrets. The discovery of deep-sea hydrothermal vents in 1977 along the Galapagos Rift revealed an ecosystem that thrived in absolute darkness, powered not by sunlight but by chemosynthesis. This finding fundamentally altered our understanding of where life can exist, breaking the long-held assumption that every food chain must begin with photosynthesis. It expanded the concept of a habitable zone beyond the narrow orbital band around a star, suggesting that oceans hidden beneath ice, warmed by internal geologic heat, could sustain life far from any sun. This revelation turned the scientific gaze toward Jupiter's moon Europa, a world whose fractured icy surface conceals a global ocean of liquid water kept warm by tidal flexing. The search for life in that alien sea now focuses on the possibility of hydrothermal activity on its rocky seafloor, where chemical reactions between water and rock might generate the energy and nutrients to support microbial ecosystems. Spacecraft missions of the coming decade aim to verify the ocean's composition and search for biosignatures that may have been carried up from the depths. The Cassini spacecraft provided a stunning glimpse of a similar ocean world at Saturn's moon Enceladus, where enormous plumes of water vapor and ice crystals erupt from fissures near the South Pole. Analysis of these plumes revealed hydrogen gas, methane, carbon dioxide, and complex organic molecules, a chemical signature remarkably similar to the fluids percolating through Earth's own hydrothermal vent systems. The presence of molecular hydrogen in particular suggests that serpentinization, a reaction between water and iron-rich rock, is actively occurring on Enceladus's seafloor, providing a potential energy source for life. On Europa, where the ocean is in direct contact with a silicate mantle, hydrothermal systems might resemble the towering carbonate chimneys of the Lost City vent field in the Atlantic, formed by cooler, alkaline fluids rather than the black smokers of volcanic ridges. These structures could rise for tens of meters, creating a labyrinth of mineral spires that host chemical gradients perfectly suited for the emergence of primitive metabolism. The gentle, persistent heat from tidal friction would drive a slow circulation of seawater through the fractured crust, carrying the building blocks of life from the rock into the deep. The study of Earth's deep-sea biology has become a direct guide for astrobiology, demonstrating that life can flourish in extremes of pressure, temperature, and chemical isolation. Organisms that use hydrogen, methane, or sulfur compounds to fuel their cells show us that the definition of a habitable environment is far more generous than we once imagined. This knowledge shifts the probability of extraterrestrial life from a speculative hope to a measurable hypothesis, framing the icy moons of the outer solar system as the most promising targets in our search for a second Genesis. Each expedition into the abyss reinforces the idea that the ocean floor is a mirror in which we see the possibilities of other worlds. The vent communities, with their blind shrimp and giant tube worms, are not just curiosities of our own planet, but templates for the alien ecosystems that may pulse in the dark beneath the ice of Europa or Enceladus. And as we listen to the quiet sonar echoes of our own deep sea, we are learning to read the faint signals that will one day tell us whether we are, or ever were, alone in the universe. Far below the reach of sunlight, where the ocean becomes a realm of perpetual night, deep-sea coral ecosystems thrive in absolute darkness. These slow-growing forests, built by species such as the branching white coral Lophelia pertusa and the pink bubblegum coral Paragorgia arborea, can be found from the dimly lit continental slopes at 200 meters down to the abyssal plains 6,000 meters below. They are architects of the deep, constructing complex three-dimensional structures that rise from the seafloor in total silence. Without the symbiotic algae that sustain their shallow water relatives, these corals rely entirely on the gentle rain of organic particles drifting down from the surface. Marine snow, a constant shower of dead plankton, fecal pellets, and other detritus, becomes their only source of nourishment. Each polyp extends delicate tentacles into the current, capturing these suspended morsels from the passing water with a patience measured in millimeters per year. The growth of a deep-sea coral garden is a story written in centuries. A single branch of Lophelia pertusa may lengthen by only 4 to 25 millimeters annually, and the oldest known reefs have been radiocarbon dated to more than 8,000 years of continuous existence. The towering bubblegum corals, with their massive gnarled trunks, can live for several millennia, making them among the oldest living animals on Earth. These ancient groves are living archives of ocean history, bearing witness to shifts in current and climate that no human has ever seen. These coral structures become thriving islands of life in the vast, featureless expanse of the deep sea. Their tangled branches offer a nursery for juvenile fish, including commercially important species like redfish and grenadiers, and a foothold for a staggering array of invertebrates. Brittle stars entwine themselves around the coral polyps, while squat lobsters, sea fans, and delicate glass sponges create a vibrant, multi-layered community. The reef acts as a vital refuge, a feeding ground, and a spawning site in a habitat where such opportunities are scarce. The greatest immediate threat to these ancient forests comes from bottom trawling, a fishing method that drags heavy-weighted nets across the seafloor. A single pass of a trawl door can obliterate a coral reef that has been growing since the last ice age, reducing a millennia-old ecosystem to a field of rubble in a matter of moments. The delicate, slow-growing colonies are scraped away, leaving behind a flattened, lifeless seabed that may take centuries to show even the faintest sign of recovery. An even more pervasive and insidious danger is gathering in the water itself: ocean acidification. As the sea absorbs excess carbon dioxide from the atmosphere, its chemistry shifts, lowering the pH and reducing the availability of the carbonate ions that corals need to build their skeletons. In waters that are already cold and deep, where the saturation horizon for aragonite is naturally shallower, this change threatens to dissolve the very foundations of their existence. A coral polyp struggling to calcify in a more acidic ocean faces a slower, more uncertain future, placing the entire deep-sea community at risk of silently eroding away. Far below the abyssal plains and the crushing weight of the ocean, there exists a hidden world that reshapes our understanding of life itself. It is a realm not of flesh and bone, but of single cells, living out their slow existence in the solid rock of the ocean floor. This deep subsurface biosphere, discovered only in recent decades, stretches for kilometers beneath the seafloor, a labyrinth of microbial life inhabiting the microscopic pores and fractures within ancient lava flows and sediments. Scientists now estimate that the total mass of carbon locked within these deep-dwelling microbes rivals that of all surface life combined. The sheer scale of this hidden biome is staggering, a vast, unseen ecosystem that operates entirely in the dark, sealed off from the sun for millions of years. Each tiny pore in the rock, filled with fluid, becomes a haven where a few cells might divide once every 1,000 years, their pace of life almost imperceptible against the backdrop of geological time. The engine driving this deep biosphere is a chemical reaction between the rock itself and the water that seeps through it. In a process called serpentinization, seawater percolates down into the iron-rich mantle rock, reacting with minerals like olivine to produce a cascade of new compounds. The most critical of these is hydrogen gas, a clean-burning fuel that certain microbes can harness, using it to convert carbon dioxide into organic matter without any need for sunlight or oxygen. This discovery radically expanded the known boundaries of life, proving that it persists not just in the soft sediments, but within the hard, basaltic crust of the ocean floor. Deep-sea drilling expeditions have pulled up cores of glassy basalt riddled with tiny tubules, the telltale sign of ancient microbes that once bored into the rock to find a chemical meal. These organisms are not merely surviving, they are endolithic, living inside the stone, a testament to the tenacity of life in the most extreme frontiers of our planet. The implications ripple outward, forcing a fundamental revision of the entire biosphere's extent. The volume of habitable space beneath the ocean floor is now understood to be the largest on Earth, a continuous interconnected layer of life that may link the buried sediments of the abyss to the deepest fractures in the crust. This subterranean reservoir plays a slow, profound role in the planet's carbon cycle, sequestering and transforming carbon over millions of years, a process we are only just beginning to quantify. To contemplate these microbes is to witness life stripped to its absolute essence, content with the faintest whisper of energy from a rock and a drop of water. They are the quiet caretakers of the deep, a reminder that the Earth's vitality extends far beyond the reach of light, into the hidden crevices of the solid planet. Here, in the dark heart of the stone, the biosphere finds its deepest, most enduring root. Far beneath the moonlit surface of the ocean, a silent archive preserves the memory of our planet. Layer upon layer of fine sediment, drifting down over millions of years, records the slow rhythm of Earth's changing climate and the sudden shocks of catastrophe. These archives are read not with eyes, but with the hollow steel drill pipes of a remarkable ship. The Joides Resolution, a vessel built for scientific exploration, serves as the flagship of the International Ocean Discovery Program. From its derrick, a long string of pipes descends through kilometers of water and into the seabed, rotating a drill bit that cuts a cylinder of mud and rock. The core is then hauled back to the deck, a delicate column of deep time to be photographed, scanned, and sliced into thin sections for analysis. Within these cores, the most eloquent storytellers are often microscopic. The tiny shells of foraminifera, single-celled organisms that once floated in the ancient ocean, are preserved by the trillion. Scientists measure the ratio of oxygen isotopes locked within their calcium carbonate shells. This ratio shifts depending on the temperature of the water and the amount of ice stored on the continents, offering a precise thermometer for worlds long vanished. The sediment also holds a stark record of life's low points. A thin, dark line in a core, often no thicker than a fingernail, can mark a moment when the planet was thrown into darkness. The boundary that closed the Cretaceous period, for instance, is rich in the element iridium, a signature of the asteroid impact that triggered a mass extinction. Below this line, the intricate shells of countless foraminifera species are abundant. Above it, most of them are simply gone, replaced by a quiet pulse of hardy survivors. This deep-sea chronicle stretches back to the childhood of the modern ocean. In the Western Pacific, the International Ocean Discovery Program and its predecessors have drilled into some of the oldest sea floor on Earth. Cores recovered from these depths have reached sediment that accumulated on the ocean floor around 180 million years ago during the Jurassic period, when the supercontinent Pangaea was still in the process of breaking apart. To hold a section of that Jurassic core is to touch a time when the Atlantic Ocean was barely a narrow rift and marine reptiles swam through warm, shallow seas. The sediments, now compressed into bands of reddish clay and chert, contain the faint chemical whispers of a world with much higher carbon dioxide levels than today. As the ship's laboratories hum quietly through the night, these archives patiently yield their secrets, a lullaby of deep time for a restless planet. In the permanent darkness of the deep ocean, sperm whales perceive their world through sound. They produce powerful clicks, among the loudest biological sounds on Earth, which can reach upwards of 230 decibels. These clicks are focused through a waxy structure called the spermaceti organ, acting as a biological sonar beam. The returning echoes reveal the shape, size, and even the internal structure of a squid half a kilometer away, a precision that allows them to hunt in absolute blackness. To follow their prey into the abyss, sperm whales perform dives that routinely exceed 2,000 meters. A single breath at the surface can sustain them for up to 90 minutes as they descend into the crushing pressure of the bathypelagic zone. Their bodies are masterpieces of adaptation, with flexible rib cages that collapse safely, lungs that compress, and muscles loaded with oxygen-binding myoglobin. In these lightless depths, they hunt the largest biomass of cephalopods on the planet. Even among these extreme divers, beaked whales push the boundaries further. A Cuvier's beaked whale was recorded diving to 2,092 meters, a depth where the water pressure exceeds 300 atmospheres. This particular dive lasted for 3 hours and 42 minutes, a breath-hold endurance record for any mammal. These elusive whales spend so little time at the surface that their lives remain largely a mystery, glimpsed only through satellite tags that briefly transmit their astonishing journeys. While toothed whales use rapid clicks for echolocation, baleen whales fill the ocean with songs that travel vast distances. Their low-frequency calls can become trapped in a natural sound channel known as the SOFAR channel, a layer of water where temperature and pressure create a waveguide. Sounds within this channel can propagate for thousands of kilometers without losing their energy. A blue whale's song, measured at around 180 decibels, can theoretically be heard across an entire ocean basin, connecting isolated individuals through a shared acoustic seascape. The movements of deep-diving whales are not random. They trace the contours of an invisible landscape of prey. By tracking sperm whales, scientists have discovered that their hunting dives target dense scattering layers of squid that rise toward the surface at dusk. These whales spend so much time in the deep that their foraging patterns mirror the daily vertical migration of the largest animal movement on Earth. In effect, the whales act as biological samplers, mapping the distribution of deep-sea life that we cannot otherwise see. The deep ocean, once thought to be a silent desert, is revealed through the lives of whales as a complex soundscape of biological rhythms. From the rapid clicks of a hunting sperm whale to the haunting songs of a fin whale traveling through the SOFAR channel, sound is the thread that binds their existence. Their dives into the abyss are not just a search for food, but a kind of mapping, a way of knowing a world that remains largely inaccessible to us. Each surfacing whale offers a brief window into the hidden architecture of the deep. In the permanent night of the deep ocean, life unfolds in ways that were once hidden from human eyes. For decades, our understanding of these creatures came from specimens hauled to the surface, often lifeless and torn from their context. The advent of remotely operated vehicles, or ROVs, has changed everything, allowing scientists to linger in the depths and witness undisturbed behaviors for the first time. In 2018, researchers at the Monterey Bay Aquarium Research Institute published a remarkable finding from 1,400 meters below the surface. A female octopus of the species Granelodon boreopacifica had been observed guarding a clutch of eggs on a rocky outcrop in the Monterey Canyon. The ROV visited her repeatedly over the course of 53 months, documenting a vigil longer than any other known animal's brooding period. Throughout that entire time, the mother was never seen to eat, even when small crustaceans passed within reach. She slowly lost weight, and her skin became pale and loose, yet she remained with her eggs, gently cleaning them and fending off predators. By the time they hatched, she had given everything. Her ultimate fate remains unknown, but her sacrifice rewrote the boundaries of maternal dedication in the animal kingdom. The same ROV technology has revealed that parental care is not limited to cephalopods in the deep. During a dive in the Monterey Canyon, the vehicle encountered a snailfish, Carproctus melanurus, curled tightly around a cluster of eggs adhered to a rock. This was the first direct evidence of a deep-sea fish actively guarding its offspring, a behavior that had previously been assumed absent from such an environment. Perhaps the most astonishing revelation came when researchers observed a 7-armed octopus, Halophron atlanticus, manipulating a venomous siphonophore tentacle. The octopus held the stinging coil in its arms, seemingly using it as a defensive tool or a weapon against potential prey. Such complex tool use had never before been documented in a deep-water cephalopod, hinting at cognitive abilities that rival those of their shallow-water relatives. These discoveries underscore a profound truth. The deep sea is not a barren realm of simple survival, but a stage for intricate and patient behaviors. Without the quiet, persistent presence of ROVs, the 53-month vigil, the egg-guarding fish, and the tool-wielding octopus would have remained invisible. Each new observation peels back another layer of the ocean's secrets, revealing a world far richer than we ever imagined. In the silent, crushing darkness of the abyssal plains, a quiet chemical war has been waged for millions of years. Here, organisms that cannot flee or fight with tooth and claw have evolved a different kind of armor. They produce molecules of astonishing complexity and potency, compounds designed to paralyze a predator or stop a rival from growing. This vast, cold pharmacy may hold the keys to treating some of humanity's most persistent diseases. Some of the earliest evidence for this idea came not from the abyss, but from sunlit shallows. The venom of a small cone snail, Conus magus, yielded a peptide called ziconotide, a painkiller 1,000 times more powerful than morphine that works without triggering addiction. In the mangrove roots of the Caribbean, a colonial sea squirt, Ectinicidia turbinata, was found to contain trabectedine, a compound now used to treat soft tissue sarcoma and ovarian cancer. These discoveries, drawn from accessible coastal waters, hinted at the untapped treasure lying deeper. Far beyond the reach of sunlight, on the slopes of seamounts and the bedrock of the continental shelf, sponges anchor themselves to the seafloor. Lacking any physical defense, these ancient animals instead synthesize a cocktail of cytotoxic chemicals to deter grazers and outcompete neighbors. One deep water sponge, Discodermia dissoluta, collected from depths of over 100 meters off the Bahamas, produces discodermalide, a molecule that stabilizes cellular scaffolding and halts the division of cancer cells. Another sponge, the glassy, vase-shaped Lisodendorix, yields compounds that have inspired a whole new class of anti-cancer drugs. The journey from a deep-sea discovery to a vial of medicine, however, is immense and fraught with difficulty. These miraculous molecules are often present in vanishingly small quantities within their hosts, making direct harvesting both ecologically unsustainable and prohibitively expensive. Trabectedin, for instance, originally required a metric ton of sea squirts to produce a single gram of the drug. Today, it is manufactured through a semi-synthetic process that begins with a compound fermented by a laboratory bacterium, a triumph of tenacity that took decades to perfect. Recognizing the enormous potential, The United States National Cancer Institute began systematically collecting and screening marine organisms in the 1960s. Their repository now holds tens of thousands of frozen and dried specimens, many gathered by submersibles from the deep sea, representing one of the most comprehensive libraries of marine biodiversity on Earth. This collection has been the starting point for countless research papers and has provided the raw material from which several approved drugs were born. Despite this foresight, the pharmacological frontier of the deep ocean remains almost entirely untouched. Scientists estimate that fewer than 1% of deep-sea organisms have been screened for any kind of biological activity. The sheer logistical challenge of reaching the abyssal plane, coupled with the delicate art of culturing these organisms in a laboratory, means that the greatest repository of natural chemical diversity on the planet has barely been asked a single question. In the eternal darkness of the Challenger Deep, nearly 11,000 meters below the surface of the Pacific, a discovery in 2018 revealed the quiet reach of human activity. A scientific survey of the deepest point on Earth recorded an object drifting across the seabed, a simple plastic bag. Found through the analysis of the deep-sea debris database, it confirmed that no corner of the planet remains untouched by our synthetic exhalations. Even the inhabitants of these Hadal trenches carry the evidence within their bodies. Researchers from Newcastle University examined tiny amphipods collected from 10,190 meters and found their guts laced with microplastic fibers. One previously unknown species, discovered during this study, was given the name Eurythanes plasticus as a direct reflection of its contaminated home. The synthetic particles had woven themselves into the fabric of life at the very bottom of the world. Such material reaches these depths by following the ocean's own circulatory system. Plastic waste from coastlines and rivers is gathered by rotating currents, which concentrate the debris into vast accumulation zones at the surface. Over time, wind and sun break the plastic into smaller fragments, and these particles are eventually carried downward by gravity, sinking through the water column like a slow, invisible snow. The most famous of these surface gathering points is the Great Pacific Garbage Patch, a diffuse yet immense vortex of debris swirling between Hawaii and California. It spans an estimated 1.6 million square kilometers and contains roughly 1.8 trillion pieces of plastic, ranging from abandoned fishing nets to microscopic fragments. This floating repository is not a solid island, but a dense, soupy cloud of material, continuously shedding particles into the deep. The pathway from the surface to the abyss is a direct conduit into the deep-sea food web. Microplastics become coated in algae and bacteria, making them smell and taste like food to small creatures, which then carry the particles downwards during their daily migrations. The bodies of these organisms, along with sinking plastic-laden fecal pellets, deliver a steady rain of synthetic material to the seafloor, where scavengers like amphipods consume it directly. For organisms that evolved over millions of years in a world without synthetic material, this ingestion poses a novel and silent threat. The plastics can leach hormone-disrupting chemicals and provide a surface for toxic pollutants to accumulate before entering the animal's tissue. In the stable, slow-moving environment of the deep sea, where life is finely tuned to scarcity, this alien influx represents a profound and deeply uncertain disruption to an ecosystem we are only just beginning to understand. In the early 1960s, a geologist named Harry Hess proposed a radical idea that would reshape our understanding of the planet. He suggested that the ocean floor was not a static, ancient plane, but a dynamic surface constantly being created at mid-ocean ridges and consumed at deep-sea trenches. This process, which he called seafloor spreading, provided the missing mechanism for the drifting continents that Alfred Wegener had envisioned decades earlier. Hess imagined the seafloor as a slow conveyor belt, endlessly recycling itself. The most compelling evidence for seafloor spreading arrived from the magnetic signature of the ocean crust. As ships towed magnetometers across the mid-Atlantic ridge, they recorded a beautiful, symmetrical pattern of magnetic stripes on either side of the central rift. These stripes are frozen records of Earth's magnetic field reversals, captured in cooling lava that emerges at the ridge axis. Just like a tape recorder, the new crust preserves the orientation of the planet's magnetic poles at the time of its birth, proving that the ocean floor is continuously generated and pushed outward. Today, the Atlantic Ocean continues to grow, its basin widening by about 2.5 centimeters each year. That is roughly the same rate at which human fingernails grow, a quiet but relentless movement that can be measured with exquisitely precise satellite positioning. At this pace, the distance between Europe and North America increases by a full meter every 40 years, a geological heartbeat that has been pulsing for over 100 million years. This constant renewal means the ocean floor is surprisingly youthful compared to the ancient continents. The oldest oceanic crust anywhere on Earth is a mere 200 million years old, a relic of the Jurassic period found in the eastern Mediterranean and the western Pacific. In contrast, the continental rocks beneath our feet can reach ages of 4 billion years, preserving a history that stretches back almost to the planet's formation. The seafloor is a fleeting skin, perpetually born and erased, while the continents float like durable rafts above the deeper Earth. The ocean's narrative is not one of endless creation. Where plates converge, the ancient seafloor plunges back into the mantle, a process called subduction that carves the deepest scars on the planet's surface. These plunging slabs drag the edge of the overriding plate downward, creating vast linear depressions known as ocean trenches. The Mariana Trench, descending nearly 11 kilometers, forms where the Pacific Plate bends and vanishes beneath the Philippine Sea Plate, a dark, cold gateway to the Earth's interior. The ocean is a geological engine, its waters concealing the fundamental cycle that shapes the surface of our world. From the volcanic birth at a mid-ocean ridge to the slow, majestic trek across thousands of kilometers, and finally to the sinking grave of a subduction zone, the seafloor is in constant motion. This great planetary rhythm, a silent dance of creation and destruction, has been running for eons, driven by the heat of the Earth's interior. It is a process that, in the stillness of the deep, never truly sleeps. Beneath the surface of the sea, light fades within the first few hundred meters, but sound travels vast distances with remarkable efficiency. In this dark realm, acoustics become the primary means of observation, turning the ocean's own properties into a planetary listening device. Scientists have learned to interpret these underwater sounds, from the deep rumble of earthquakes to the delicate clicks of a hunting dolphin, transforming the ocean itself into a vast sensory network. The most sensitive of these networks is the International Monitoring System, deployed to verify the Comprehensive Nuclear Test Ban Treaty. Deep ocean hydrophones suspended in a layer of water known as the SOFAR channel, where sound can travel for thousands of kilometers, listen for the distinct acoustic signature of an underwater nuclear explosion. These stations, anchored in some of the most remote waters on Earth, can pinpoint a detonation with astonishing precision, distinguishing a man-made blast from the immense repertoire of natural sounds. While scanning for forbidden nuclear tests, the hydrophones of the monitoring system made an unexpected and profound contribution to geology. They began recording the groans and shudders of the planet itself, submarine earthquakes and volcanic eruptions that had previously occurred in complete silence to human ears. Analysts detected the low-frequency rumble of a spreading seafloor thousands of miles away and the sudden, violent creation of new volcanic islands, providing a real-time chronicle of the Earth's restless tectonic activity. The same quiet listening technique, known as passive acoustic monitoring, has revolutionized the study of marine mammals. For decades, researchers have lowered hydrophones into the blue to eavesdrop on the haunting songs of humpback whales and the metronomic clicks of sperm whales. By recording these vocalizations over long periods, scientists can track the seasonal movements of great whales across entire ocean basins, estimate the size of hidden populations, and begin to understand the intricate dialects of these intelligent beings without ever needing to see them. Sound also offers a remarkable window into the ocean's changing climate. The principle of acoustic thermometry is simple. Sound travels faster in warmer water. By transmitting a low-frequency hum from a source and measuring the precise time it takes to arrive at a distant receiver, scientists can calculate the average temperature of the water column along that path. The Acoustic Thermometry of Ocean Climate Project, which began in the 1990s, used this method to detect a gradual warming of the deep Pacific, providing independent confirmation of the planet's growing heat content. All of these natural and scientific sounds now compete on a global ocean noise map, a chart of anthropogenic sound that reveals the true cost of our industrialized seas. The ever-present thrum of commercial shipping, particularly along the Great Circle routes of the Northern Hemisphere, has raised the background noise level in many regions by a factor of 10 in the last century. For marine mammals, this chronic noise shrinks their sensory world, masking their communication calls and increasing stress, a silent disruption that is now a primary focus of conservation efforts. Scattered across the world's oceans, A fleet of specialist research vessels forms a quiet network dedicated to the planet's last great wilderness. Ships such as the American RV Atlantis, the German RV Sonne, and the Japanese RV Shinkai 6500 are equipped with dynamic positioning systems that hold them precisely over a point on the seafloor, sometimes for days at a time. Their deck hangars shelter remotely operated vehicles and human-occupied submersibles capable of descending to the deepest trenches, while multi-beam sonar arrays paint the unseen topography miles below. These vessels are self-contained islands, carrying enough fuel, food, and scientific equipment to remain at sea for weeks without sight of land. To keep a multi-million-dollar deep submergence vehicle in the water for as many hours as possible, the human crew and science party operate on a continuous rotation that never lets the laboratory fall silent. A typical watch schedule divides the day into two 12-hour shifts, with a brief handover period where the outgoing team briefs their replacements on the dive's progress and any technical anomalies. Bunks are tucked into narrow, windowless cabins, curtained off from the 24-hour fluorescence of the corridors, and scientists learn to sleep in 4-hour blocks, lulled by the steady thrum of the engines. The rhythm is disorienting at first, but the body slowly adapts, trading the cycle of the sun for the far more urgent cadence of the abyss. To work in the main science control room is to inhabit a space without a horizon. The room is windowless, its walls lined with screens displaying sonar returns, navigational charts, and the live video feed from a machine suspended in eternal night. Beneath the hull, the seafloor may lie 4,000 meters down, a depth that would crush a human body in an instant. Yet the only immediate sensation is the hum of servers and the faint scent of recycled air. Psychologists have noted that prolonged immersion in this artificial environment, with no natural light and no visual reference to the outside world, can induce a subtle dissociation, a feeling of floating in abstract space rather than sailing on water. The mind compensates by anchoring itself to the luminous stream of data, the only evidence that something vast and real is unfolding just beneath the steel deck plates. Then, in the early hours of a mid-watch, the monotony breaks. The ROV's spotlight catches a form that does not match any entry in the onboard identification guides, and the control room gradually falls still. A biologist leans closer to the monitor, her voice dropping to a murmur as she describes the movement of a translucent, gelatinous creature that has never been recorded by human eyes. There is a particular quality of silence in these moments, a collective holding of breath, while the camera zooms in and the first high-resolution still images are captured. For the scientist who has spent years studying family trees built from sparse museum specimens, seeing a living holotype drift past the lens is a moment of quiet, almost private reverence, a privilege granted by the ocean alone. Such discoveries are rarely the work of a single nation. Modern deep-sea expeditions are mosaics of international collaboration, stitched together by shared ship time and the free exchange of expertise. A cruise might be led by a British university, use a German-owned ROV operated by a Canadian team, and host taxonomists from Japan, Chile, and South Africa, all working under a permit issued by a Pacific Island state. Organizations like the Interridge Program and the United Nations Decade of Ocean Science for Sustainable Development have codified this spirit, ensuring that the expensive, logistically daunting task of exploring the abyss becomes a genuinely global pursuit. The result is a flotilla of researchers who speak a common language of coordinates, genetic sequences, and wonder, bound together across national borders by the shared understanding that the deep seafloor is humanity's common heritage. The deep ocean remains the last great wilderness on our own planet, a realm of crushing pressure and perpetual darkness that begins where sunlight fades and ends in trenches deep enough to swallow mountains. It is the largest living space on Earth, yet we have glimpsed perhaps a fraction of 1% of its total volume. To stand at the edge of this knowledge is to accept that the majority of our world is still a stranger to us, a vast, contiguous ecosystem that dwarfs all terrestrial habitats combined. We have mapped the surface of Mars in exquisite detail, tracing every crater and ancient riverbed, and charted the moon's far side with a completeness that leaves little to the imagination. In contrast, only about 25% of the entire global seafloor has been mapped to a resolution that would allow us to discern a large building. The rest remains a blur of interpolated data, a coarse sketch where entire undersea mountains and trench systems await their first cartographic line. The specimens already lifted from the abyss tell a story of overwhelming abundance. In the archives of museums and research institutes, There are hundreds of thousands of deep-sea creatures preserved in jars, many of them collected decades ago, still waiting for a taxonomist to give them a name. It will take generations of dedicated scientists simply to describe what has already been brought to the surface. A quiet, meticulous labor that unfolds far from the spotlight, one delicate illustration at a time. The ocean resists the human sense of time with a patience that is geological. A single sponge on a seamount can live for 11,000 years, its tissues growing so slowly that a century passes like a single breath. The cycles of deep-sea currents, the formation of a manganese nodule the size of a pea, the drift of a whalefall community from bloom to barren bone, all obey rhythms that make a human lifetime feel like a fleeting spark. We cannot rush a world that operates on a clockwork of millennia. To study the deep is to be schooled in humility, to confront a system so vast and so intricately layered that certainty dissolves into a sea of questions. Every expedition reveals organisms that defy our categories, from octopuses brooding their eggs for over 4 years to microbial communities thriving in rock fissures 1,000 meters below the seafloor. The ocean teaches us that our presence is not a culmination but a brief, quiet visitation, and that the most profound act of discovery is often simply to listen and to be still. Being at the beginning of understanding the ocean means holding a map that is mostly blank space, knowing that what we do not know is immeasurably larger than what we do. It is a rare privilege, this frontier state, where a single cast of a net can pull up a creature that no human eye has ever seen. We are the first generation to have the tools to truly explore this hidden hemisphere, and yet we are only learning the first words of a language that has been spoken here since the world was young. As you rest here, the shapes you followed through the deep begin to settle into something less like knowledge and more like a remembered dream. The siphonophores' drifting chain of light, the whalefall's slow city of transformation, the abyssal plain stretching beyond any single lifetime. They do not ask to be catalogued now. They gather instead as a quiet weight, a sense that the world beneath the world is endlessly patient, and that you have been permitted, for a little while, to float beside it. This is the tender ache at the center of all human looking. We point our instruments into the dark water, not because we hope to map every trench, but because the unknown pulls at something ancient and restless in us. The ocean keeps its secrets the way the night sky keeps its distances, and in that withholding there is a strange companionship. We are drawn to edges, to the place where the known dissolves, because that is where we remember how to wonder. Let that wonder now become a stillness. The midnight zone still glimmers beyond reach, and so does the morning. The long migration of sound through the deep scattering layer, the faint bioluminescent pulse you heard, these continue without your attention. You can release the need to understand. The tide of your breathing can slow, drawn by a gravity older than thought, into the quiet fathoms where sleep begins. The ocean does not wait for us to understand it. It continues in the dark, at its own pace, indifferent to the instruments we lower into it and the questions we carry down. Somewhere below the surface, a creature is moving through water that has never reflected a single photon of artificial light. It knows nothing of the world above. It is simply there, in the cold and the pressure and the silence, alive in a way that does not require our knowledge of it. What we have found so far has only deepened the silence around what we have not. The ocean keeps its own count. We are still at the beginning. Let the dark water carry you now. There is nothing left to solve tonight. The ocean holds its secrets gently, without urgency, the way sleep holds you, quietly, until morning.